So are you going to show us the results?
No, we're reading, so we're referring.
Oh, okay. Okay.
I'll show you leading up to the result.
Okay, yeah.
Will you give me 10 minutes also?
Say it again?
Will you tell me 10 minutes also,
10
just so I know?
minutes, 10 minutes.
Yeah. Thanks. Oh, is my thing on?
Let me ask, where is, you see, ah, ouais. J'ai besoin de l'éteindre.
Pour l'éteindre. T'as un minute ici?
Oui.
Faut l'éteindre.
D'accord.
L'écran est censé s'éteindre. Si. Pardon, ouais, si. Hello. Okay. Just want to make sure it's on. Feels like old times.
Okay, good afternoon, everyone. So we'll start our afternoon session with Dan Skolnick from Duke University. He will tell us about the importance of self-consistency for measuring the Hubble constant.
All right. Thanks, everyone. Thanks for coming back from lunch. I'm really happy to be here and see so many familiar faces. I'm in North Carolina now, which is the American South, so this heat is nothing. It doesn't feel bad at all. So I'm going to talk about new results from the different collaborations I'm part of, SHOES, PanSTARRS, Dark Energy Survey. But I want to just deliver my take-home message because it's what I spend most of my time thinking about. So that is to do the distance ladder, and this is a plot that I think everyone's seen now, where you use some geometric method to calibrate Cepheids to calibrate supernovae, and the supernovae to measure the Hubble constant. The key thing in this process is that you just do things self-consistently. So as long as you're doing the same thing in these two rungs or these two rungs, then you're going to be okay. But you have to spend a lot of time really thinking about how the filters and the 0 points and fitting methods and any higher order corrections, you're doing the same thing. And the kind of the beauty of the distance ladder approach comes from certain systematics canceling out as long as you do the same approach for the first two rungs or the second two rungs. So that's my take-home message, and I'm just going to keep hitting this point of self-consistency. But before I get into the local distance ladder measurement, I want to talk about Pantheon, since that's my baby. Mike Turner at Chicago, he has this thing that he'd always tell me that supernova cosmology has warts, but it doesn't have cancer. So I don't know if he says that about everything or just supernovae, but this kind of shows that all of our stuff is public, it's accessible, and so these were the original supernovae used to discover the accelerating universe. This is a plot from the Pantheon paper, and we've gone from these large contours to here. So Pantheon's now 1,000 plus supernovae. Tried to calibrate the entire thing in some homogeneous way, we keep improving things and keep finding problems, but things keep getting better. All right, now from Pantheon, this places the tightest constraint on dark energy to date, consistent with the cosmological constant. There's a number of papers coming out almost every night looking at something or finding something. So I want to address a few small things. So there's this one paper that that's gotten a lot of attention recently, which tried to recast the H0 tension as omega M tension. Basically, they took the Pantheon sample and cut it down to a really small omega matter, a really small maximum redshift. And then they say, like, at some specific redshift, they find 3 plus sigma tension with Planck, and that's somehow related to the H0 tension. The connection doesn't make much sense to me, but importantly, they didn't include systematics at all in that analysis. So if you do, it's a little over 2 sigma at one specific redshift. So I don't find that big of a deal. I had a problem on my end. I extrapolated some peculiar velocities. This affects W at a very small level. There's also been a paper recently that said that Pantheon and JLA redshifts were different, and this means no one should trust supernovae at all. The reason for that was just that JLA used the supernova redshift instead of the host galaxy redshift, but there's a very small problem. So I don't find that so bothersome. Okay, so those are just 3 things I want to get off my chest quickly. All right, now when Pantheon has been down, I'm seeing in a lot of papers, you can see certain curiosities or funnies or whatever you want to call them. These are expected. So this is a kind of systematic plot. So it's showing different systematics, the impact of each of them. And you can see on the 1 to 2% level, there's correlations. And for those of us who work on this, we spend our time trying to beat these down. But those are absolutely in our data. And with regards to the H0 tension, this is still on the order 10 times smaller. So H0 tension is roughly 0.18 mag or so. So this is 0.01 to 0.02. So the kind of funnies that you see in Pantheon still can't mess too much with the H0 tension. All right. Now, one of the big things about Pantheon that made it different than past studies like JLA is we do this method called BBC, where we basically try to forward model the expected distance biases in the data. So past studies, if you look at your Hubble residuals, which is on the y-axis, versus your supernova color or your supernova width, you'd see these trends. And it turns out from the sample itself, if you just solve for the underlying populations, basically you think that there's some narrow population and it scatters out because of noise, then this is exactly the trend that you expect. So just from simulations that match your data, you get the same exact trend, and you could take this out, and now it's like 15 sigma. So it's very much in the data, and I'll talk about all these host galaxy effects later. They're all much smaller than this. So this is kind of a big thing that we try to take out and reduces the dispersion, and it's expected. This is what it should look like. Okay, now in a few papers I've come out recently, there's been some confusion about model dependence of Pantheon. So I know a lot of people outside the supernova community will just take these big data sets and kind of run with them. And there's this question of, well, how model dependent is Pantheon. So with Pantheon, I tried to do something to make it really nice for the community, which is I just gave redshifts and distances and distance errors. I thought that would make it easier for everybody, whereas JLA kind of gave all the light curve parameters, and you have to solve for the nuisance parameters. Now, when I give the distances, those distances are found by simultaneously solving for the nuisance parameters and the bias corrections I talked about in that BBC slide, and kind of does this in this iterative process, and then it loops over the best fit cosmology, and it bins over redshift. So it's trying to take out all the cosmological dependence. So what I try to deliver is trying to minimize all the cosmological dependence. For JLA, while you're solving for alpha and beta, there is this same kind of bias correction, though they just do it with redshift, but that's a fixed value, so it doesn't depend on alpha and beta or your cosmology. While you're changing your alpha and beta, your cosmology, you're not changing this number. And so in that sense, there's kind of more of that same model dependence in JLA. So just because I try to not give this information, like give it in other files, doesn't mean that I have more model dependence. It's just that I've tried to take it out so it's all done in one simultaneous way. So that's technical, but this has kept coming up. All right, now I work on both the measurement of H0 and the measurement of W. I find W way harder, and that's because for W really to do this well, you're looking at differences between a redshift of 0.05 and 0.5, and you have to measure things down to about the 1% level. For H0, you care, in terms of kind of tension type terms, about 4%, and you're comparing supernovae as 0.005 and 0.05. So the supernovae are much more similar here, between very low redshift and low redshift than these supernovae to these supernovae. So the systematics are way worse from here to here than they are, from here to here. So in that sense, W is easier. Okay. Now, for shoes, there's just a recent release, and the release wasn't new calibrator supernovae. It's just that there's a new Lmc Anchor Measurement. And with that measurement, there are also Cepheid observations of the Lmc, and things were tied together in kind of self-consistent calibration, and that moved H0 up a little bit. Now it's 74.03 plus or minus 1.42. This is now 4.4 sigma discrepant with Planck, and all the excitement is about, does that mean physics beyond lambda CDM? Now, kind of one point about this for shoes is that our sample, at least the next one that'll come out, and kind of how we do things, it's complete for all late-type host galaxies. So basically anything that is nearby that would be in a galaxy that hosts Cepheids, we include in our sample. So we are complete to that extent. So this just shows the same distance ladder. Okay, now one of the worries that I have particularly about the H0 measurement is just that we have to use a number of different samples, the supernova samples, because we go back a number of years because there's just not enough of these very local supernovae. So this plot shows the relative H0. So this is percent difference in H0 for all the different supernova samples we have in. In red, this is what we had for R16, and since that paper, there's now been a foundation release, a new CSP release. CSP kind of moves things 1-ish%, foundation's a little bit the other side. So we'd be shifted, if we do this again right now, by 0.6% or so in H0. But overall, there's actually pretty good agreement between the different samples. Remember that CMB is 9% away or so. Okay. Now, Wendy's going to talk all about this, so I just have one slide. And so there's been some output from Wendy's team and others about measurements with TRGB. So there's a postdoc in our group that's trying to look at the calibration of this. Wendy has a much bigger data set than what's out there, so I look forward very much to what she has to say. But if we try to use specific calibration, this is from this Ogle photometry and reddening that Ogle also used, what we get in the end is H0 from TRGB and from the Cepheids as similar. Again, this is limited, so I don't know, and this is what Wendy says is the number I most care about hearing. But from our checks, things look similar. Okay. Now, how can we improve the robustness of our H0 result? All right, so we do the standardization. I do this BBC process, and what has gone on in the supernova community is that after people do the standardization, they're left with these Hubble residuals, and the Hubble residuals can correlate with the host galaxy property, and that means there's some extra physics going on. Now, this can bias H0 depending on the size of the correlation and whether your host galaxy demographics are different between here and here. So we don't want that. Now, what we also don't want is to use some other sample to find whatever this correlation is and then stick that in, and then basically that introduces a step into our data. So what we ultimately want is just to be as insensitive to some extra leftover correlation that could be in our data. So I'm going to get into this kind of back and forth that our team has had with Mikkel. But I want to say two nice things about Mikkel. So one is, I think his work has really pushed us to really sharpen how we make our measurements more self-consistent. And two is that we take his work extremely seriously. You can see that because we write a paper every time he says something. So that's quite a privilege that I think he gets. All right, okay, so let's get into it then. All right, so there's now a long history between kind of Mikkel's group and our group. So this is a kind of detailed timeline. Basically, in 2010 or so, teams started noticing that there's this leftover correlation between Hubble residuals and galaxy properties. The famous, most popular one is the host mass. That's what we use in our shoes analysis, or have used so far. So then Mikkel wrote a paper saying that actually the real step is local star formation rate, and he used private supernova factory data to do it. Then in 2015, he confirmed this result with public data and found that this would change H0 to 70.6 from 73.5 or so. So this would be a big deal. And so far, this has been the kind of one paper about how H0 would change. All right, so then our side, or me and Adam Rees and Dave Jones, we looked at the public data with the latest light curve model, and we found no step. It's precisely 0. So then there's this other paper by Roman et al., and they use public data, and they were looking at a slightly different step, this local color, and they found a significant detection, but at low redshift, not significant detection. Then Mikkel has another paper saying that this local star formation step is actually small because of various changes. So that kind of agrees with what we found. But actually, the real step is local specific star formation. And this is a big step. And then we wrote another paper saying, OK, we're looking at both local color and local specific star formation. And for both of them, we don't see anything. Or it's not that significant, not that big. So that's the long back and forth. So I only have one actual issue with this whole process. So that is, from the supernova factory data, this is what's motivating all of this. My issue is just that it's not public. So this is data taken from 2005 to 2010, and we keep hearing a couple months, but we can't reproduce this or analyze this ourselves. So my analogy for this is like if WMAP was saying there's some strange foreground in Planck data, and Planck doesn't see what that signal is, but then WMAP won't release the data. So that's to me the problem now. Not anything about the analysis. It's just that we can't do it ourselves, and when we check our own data, we just don't see it. So what you might hear is that, OK, well, there's this Roman paper, and the Roman paper does use public data, and it's a slightly different effect, but it confirms the step. The problem is that if you look at low redshift, the step is minus 0.049 plus or minus 0.0462. So it's 1 sigma away from 0. And for that 0.16 number, that's 2.5 sigma. So it's actually away. So it's actually much closer to 0 than this local specific star formation step. So and low z is where we do the H0 measurement. So I don't think there's anything like a confirmation yet. But we can look at this ourselves, so that's what we do. And we do the local star formation, we do host mass, we do host color, we just try everything. And basically, this is our summary table of a paper that was published. Basically, what I was saying is it depends, the bias depends on the step size that you find in your sample and the relative demographics of your Hubble flow set compared to your calibrator set. And you put that together, and this gives your delta H naught. And for delta H naught, you could see that they're minus 0.28, minus 0.44. But remember that the tension is delta H naught of 7 or so. So these are all 10 times smaller than the big tension. They're much smaller. But still, these are something, and we want to do better. This is what I said about kind of Mikhail inspiring us to do better. So I said that how we select our galaxies that are local is that we look at we're complete for all galaxies that host Cepheus, so basically they're light-type hosts. So what we should have done last analysis was just use galaxies in our Hubble flow sample that are late-type hosts. And we could look at this Anderson paper that has these local H-alpha measurements that should be a similar kind of tracer. And what we see is that if you do it, then all these local measurements look very similar between your calibrator set and your Hubble flow set. So if we implement this, then I showed you this part of the table before, but basically we're going from this delta H naught to this delta H naught. So actually, some of the biases flip on H naught. This goes from minus 0.28 in the reduced tension direction to increase the tension direction. And the other ones, like local specific star formation, local color, they roughly have. So by doing something that we probably should have done to begin with, which I think is the right thing to do, just cut on late-type hosts so you're self-consistent. This reduces the possible bias depending on which step is the right step to 0.2-ish level when the tension is delta of 7 or so. Okay, so that's all the local color. So there's another paper by Burns et al. So this is part of the same team that Wendy's a part of. We get pretty good agreement with them. They have this nice thing of they could use the near-infrared data. So they do a few things I think that could change things compared to what we do. So they use CSP supernova for the Hubble flow set, and then a kind of mix of samples for the calibrator set. And we try to kind of keep the mix relatively the same. They do this linear correction with mass, and that because basically they have very few low mass objects or low mass hosts. The correction can be pretty big, and then for the Hubble flow set, it doesn't do peculiar velocity corrections. So that we stay within about 0.5 kilometer per second per megaparsec is pretty good. And when they go into the near infrared, actually the agreement is better, and you have less sensitivity to these host problems. All right, so Suhail will talk, I think, later this afternoon. So he also led a study using near infrared data. They also get very good agreement, 72.8 plus or minus 1.6. This has its own issues because in near infrared it's hard to understand the scatter, but overall looks pretty good. All right, now one just really fun thing is that I think there's just a lot of confusion about what host property is driving things. And with DS, we have this big sample, and we actually have quite a number of galaxies that hosted 2 type 1a supernovae. So these are the light curves of, I call these supernova siblings. So basically, they have the same parent galaxy. And you can see the light curves actually aren't that similar in a lot of cases. So even though you have the same host galaxy, they still can be quite different. And we can start placing limitations on what imprint the hosts can have on the supernovae. And this, I'm hoping to have a paper out by the end of the summer. All right. Now, another issue that keeps getting raised is, okay, well, what if we live in some just giant void, or I don't know, kind of giant void? Now, the one easy way to look at this is just you can look at the Hubble residuals as a function of redshift. So this is shown as terms like the H0 intercept. And you can see it's actually very nicely flat, whereas the models that suggest some kind of big void should be something like the blue. So we can actually measure very well how void-y of a universe we live in, and it just does not seem very void-like. So that's good. All right, now I think part of what's happening is that these measurements of the void, not with supernovae, they're using just fractions of the sky, so their models are incomplete. Supernovae actually do have similar problems in that a lot of the surveys are in the north. We're not that complete either, and that does increase our sensitivity to systematics, but the variance that we see as supernovae is consistent with simulations, which is that H0 should change of about less than 0.5%. All right, now recent DS results came out. Those were in good agreement with Pantheon, which is good. And what's nice about DS and Pantheon is that both now have been used to do a BAO reverse distance ladder. And for both Pantheon and DS, if you do that, you get a low H0 in good agreement with Planck. So if you calibrate supernovae with BAO, you get low H0, whereas if you calibrate supernovae with Cepheids, you get high H0. And this is only going to get better. I'm working on kind of DS plus Pan-STARRS photometric samples, and we're going to get to about 4,500 supernovae. So this will be huge, and we can make these measurements really well. And Sherry will talk later this afternoon that you could also do a strong lens plus type 1a supernovae. So multiple papers have come out on this just in the last few weeks of using JLA or using Pantheon, and you could see this is lens plus type 1a supernovae. Here's Planck. So if you use lens kind of distance ladder with type 1a supernovae, you get high H0. So to put this all together, basically, this is my conclusion. If you use Cepheids plus supernovae, you get a high H0. If you use strong lens plus supernovae, you get high H0. If you use BAO plus supernovae, you get low H0. And they both kind of fit along the kind of shoes versus Planck thing. So it's getting hard to think how some systematic can make this all happen together. This just seems hard. Supernovae are a good middleman, but it's the same middleman, so it's unclear kind of how they could pull this off. So we're working our way to the next big shoes analysis, and the big thing is that we'll be doubling the calibrator set sample, and we're open to all systematic checks. So if you have a problem with what we're doing, let us know now, because these things get reanalyzed like crazy. And just for the theorists in the room, I say that yes, it's true that there's not some perfect theory, it seems, that can explain all this tension, but we also still don't understand dark energy or dark matter. So I think all of us should be pursuing all avenues at this point. And I'll leave it there. Thanks.
All right, thank you, Dan, for a great talk. Any questions for Dan?
You mentioned you had systems with multiple supernovae. How consistent are the distances when you do that?
Yeah, so I'm working on that right now. I give the distances, it's hard to see, it's that last number. They seem like they're as different as any two random supernovae for that redshift. For that redshift. So I think that the galaxy is limited in kind of its role in this, but I'm not 100% about that statement. But that to me is the most interesting question.
So have you compared early type and late type hosts then?
Early type and the late type hosts. So not here. There is another one of these steps there, but it's on the smaller side compared to these other steps I've talked about. Yeah.
Sorry. Dan?
Yeah.
So you mentioned that you've got a paper forthcoming.
Yeah.
So what new, do you have new HST Cepheid
Yes.
photometry?
Right. So that's.
So for how many?
Yeah. So basically, if I show the distance ladder, so the main work is on this middle. It's really entirely on this rung. So here we have 18 hosts that have Cepheids and supernovae, and we're going to 38. So this is now the top statistical uncertainty is you're basically driven by your supernova distance uncertainty because you only have 18. So we'll divide that by √2.
Can you publish all of the photometry,
Yes.
including outliers?
Yes.
Next
Including
time.
outliers, you got it. Yes.
Okay.
Yes. We have learned that everyone wants everything, and everyone's going to get everything.
Good.
Yeah.
I have a question concerning your corrections for peculiar velocities.
Yeah.
Am I right that you corrected for them by estimating what the density field is and the corresponding acceleration field and so?
Yes.
But we know also that peculiar velocities are actually very, very large scale and do not only depend on the very local density field. How do you deal with this?
Right.
And how big are these corrections?
Right. So we use these corrections. We use an outer redshift of 0.06. They're based on the 2m++ 2 mass fields. And this is this Carrick model, but it's good to roughly like 200 kilometers per second. So it can't go that local. We basically just have to add some uncertainty. So we use the best models out to redshift 0.06, and we then just add an additional uncertainty because there are limitations for our kind of large-scale correction. That's the best we could do. I would love if we could do better. If you could do better, then you could do H0 from this step, but we don't have, that seems hard.
So I was interested in your statement that the TRGB and the Cepheid distances agree really well, because they did agree really well until your 2019 paper.
Yeah.
I thought.
So this is work by a postdoc in our group, and it's trying to use the new Lmc Anchor, and there's some choices in here that are specific. So it's this ogle photometry, and then the big question was, what do you do about the extinction? And we're using basically the same thing that the Lmc analysis did and that ogle relies on. But those two choices seem to move things around, and that's the extent of my knowledge here.
All right, let's thank Dan again for a great talk and great discussion. And the next speaker will be Michael Rigaud, who will discuss the relevance of local environment for the H0 tension.
Here.
Okay. Can you hear me well? Yeah, okay. Indeed. Okay, well, thank you for the invitation, thank you everyone, and thank you, Dan, for this very nice introduction of my work. I barely have to present anything now. I'm still going to present something. So this is the Hubbard diagram, so I'm going to go quickly here because Dan did a lot to explain that again. So this is not the very nice plot from Dan, even though it is the amazing work they have done with Pantheon. And actually, for all the things which is host or, let's say, supernova oriented, I think the work done with the Pantheon team is just exceptional, and I think it's really, really good that we push that far for supernovae. And it's because supernovae are now such a mature probe, and we have worked so much in supernovae, and it is now such a good probe that we start to see the small details, and that the small details start to matter. So this is a Hubbard diagram showing you redshift and distance modulus, and what we're interested in today is this part here, where the distance modulus only depends on these four cosmological parameters, time, the average humidity of the supernovae, and the whole game of shoes, even though, sorry, it's again an introduction of that, is to disentangle those two things, and to do that, I'm going quickly here because you heard that, the whole game is to use Cepheids to do this measurement so far, so things are changing now, but so far we are using Cepheids, and Cepheids, to remind you, this is bright young stars, it has this pulsation-humidity relation, and so you measure this pulsation inside galaxies, and if this galaxy happens to be a host of a type 1a supernovae, you know the distance of this type 1a supernovae, and you use that to extract the average humidity of the supernovae, and you include that back in the Hubble flow sample. Actually, you fit everything at once, but the spirit is this one. You get this value from Rees et al., which is roughly 74, and this is a 2% measurement. And as you know, this is to be compared to Planck data, and this is, which is really model dependent, and I'm skipping that. We have a 4.4 sigma tension. So everything here is about the question, is this new physics or is this systematic error? And I'm not going to mention any model because you know more than I do. So I'm going to focus on the systematic that Dan just mentioned, the host one. And here I would like to highlight that, again, CMB and supernovae are in complete agreement. So this is a Pantheon and Pantheon data with GLA or Pantheon data, and with respect to this time the Hubbard diagram coming from Planck. And if we do that, then we see that the residual is excellent. And there is absolutely no tension between type 1 supernovae themselves and Planck. So it's one important thing to say, that we don't have a Planck versus supernovae fight. Supernovae as a Hubbard diagram, let's say relative distance measurement from supernovae, not absolute distance measurement, but relative distance measurement from supernovae are in complete agreement with Planck, so there is no tension here. We can even see that with the plot just shown by Dan, that if we now anchor the supernovae not in the Cepheid. So you don't do the direct distance data, but you anchor the average emission of the supernovae on BAO scale. Then you, again, have a really consistent value of H0 with respect to Planck, but in tension with the direct measurements. So the only thing I want to say here, or the thing I want to highlight here, is that the only moment the story breaks when we go from Planck to direct measurement H0 is when you go from Cepheid to supernovae. Because, I mean, this is not my expertise, but if you go from geometry to Cepheid or geometry to TRGB or the probe, it seems to be consistent. So I think what Fred is going to present. But when you go from, the only step that is breaking is when you go from Cepheid to supernovae. And this is raising an issue that we don't know what type 1a supernovae are when we do this. So it's really important to keep that in mind, that even though type 1a supernovae is an amazing probe, and I've been working with that for a long time now, and we had amazing success in type 1a supernovae cosmology, it's important to keep in mind that we still don't know exactly what type 1a supernovae are. We know it's a white dwarf exploding, but we don't know how and why this white dwarf is exploding. And we don't know, for instance, how the properties of the star exploding, what I'm going to call the progenitor, how those properties are influencing the explosion mechanism, and how properties such as the age of the progenitor or the metallicity of the progenitor or any astrophysical thing you may imagine is inside the progenitor, how this is affecting the explosion mechanism and how this is then affecting the way the brightness of the supernovae peaks, and so the distance we get from that. So we know it's extremely stable, we see that, but we don't know the small details that may matter. And because the models are not yet good enough to explain what type 1 supernovae are, we may want to use proxies to measure the properties of the progenitor, and for instance, using the galaxy where we see the supernovae. And this, again, is the whole game here, is try to find a proxy for the properties of the progenitor itself. So if we look at global galaxy, for instance, with global properties, we make as a question, are type 1 supernovae from spiral or elliptical galaxies the same? And if they are, then it puts upper limit on the potential variation, but if they are not, then we know there is something in there. And the first thing people did, because actually it was one of the easiest things to do, is to measure the total mass of a galaxy. So here what you see is the residual, the Hubble residuals, so the brightness of the supernovae relative to the average emission of the supernovae. On top you are fainter, on the bottom you are brighter. And this is a binned version of that, so I'm going to show here. You see that supernovae from low mass hosts, so below 10 to the 10, are significantly fainter than supernovae from high mass hosts. And this is what people are calling the mass steps that are included in any cosmological analysis so far. So from Pantheon, on CHOOSE, or on GLA now. So we see it, but we don't understand where it's coming from. And the problem with galaxies is that global properties like that is that we don't know the source of that. We don't know why we see this effect. And if we don't understand why we see this effect, it might be a problem to know how to correct for it. And how does this effect change between samples or between redshift, as a function of redshift. So it's important to try to go one step further and trying to understand more where this effect is coming from. And to do that, what I did is not to look at global properties like that, but to look at the local environment where we see the supernovae. And basically, we are going to use the star around the progenitor to see if the cousins of the progenitor are a better tracer of the properties of the progenitor itself. And what I did is I looked at the 1 kiloparsec scale here, and you see that in this case where we have this amazing type 1 supernovae from M101, it happens to be here on an arm of star-forming area. You see all those blue stars, those are young stars, and it's exploded here. And we may ask the question, would the supernovae have been the same if it had exploded here, where you have many more older stars? This is why it's redder. Okay, and to measure this, we use an IFU. So an IFU, for those who don't know, instead of having just an image with pixels, for each pixel, which are slightly bigger, we don't have one value, we have an entire spectrum. And so from IFU images, so this is SDSS images, we see here the field of view of our IFU, and if you zoom here for the part of the spectrum with H alpha, so what we call H alpha map, we see that in this case, the type 1 supernovae happen to in a bright H alpha area, so it means there is a lot of young star in this area. And in this case, we don't have a lot of star formation, so we don't have young star in this area. So I'm not saying this one is actually young or old, and this one either, because we have projection effect. But most likely, this one is younger than this one. And to know that, to do that even slightly more accurately, this is the difference between what Don called the local star formation rate and the local specific star formation rate, which is all the things that matter. The local star formation rate here is just telling you the number of young stars I have there. Okay? But I may also have a lot of old stars at the very same place. And if I'm only looking at local star formation rate, like I did during my PhD, and I'm sorry, that's my bad, we miss an information, which is a fraction of all stars you have at this very same location. So ever since, I progressed and I learned more things. And I divide now this very same map by doing the same map with the mass. So you can measure at local masses, which tells you the number of all stars you have at this very same location. And if you do the ratio of those two things, the H-alpha map and the mass map, if we say, then you have the local specific star formation rate. And this is telling you the fraction of young stars you have at the supernova location. And this is the key information you want to have. The fraction of young stars you have. If you have a lot of star formation, if you have a lot of young stars, then you have a higher probability to be young progenitor. And if you have no young star, you know that you're not a young progenitor, right? And what I would like to highlight too is that when you go local, you see that here is globally, if you look just at the environment globally, like you see these are two spiral star-forming galaxies, relatively the same mass. But you have, when you go local, you have a completely different picture. And this is where you see the strength of going local. So, okay. So we've made this local specific star formation rate, and we compare that to the Hubble residual. And this is what we see. So this is the map, the plot Dan has presented. And we see here the Hubble residual again. So if you're on the top, you are fainter, and if you're on the bottom, you're brighter. And this is a fraction of young stars at the supernova location. That's really, by definition, the fraction of young stars at the supernova location. And we see that we have this really strong 6 sigma step. This 0.16 magnitude difference between supernovae in young environments, the young progenitor or the prompt progenitor, and those are significantly fainter than the supernovae from old environments. So we see that in our sample, and about 140 supernovae, and it's a 6 sigma step. But as Dan mentioned, we are not the only ones seeing it now. The GLA samples, the SNLS/SDSS sample, have seen it too. So this one, so be careful here. I'm looking the local specific star formation rate from H-alpha divided by mass. And here they're using a proxy for that, which is a U minus V color. And I'm going to come back to this issue because it's really important. So the U minus V color is another probe of the fraction of young stars at the supernova location, except that blue stars are young and red stars are old, so the old ones are on the right. And they also have this step. And that mentions that it's not so important. It's really important to compare apple to apple and to stay on the same sample. And I do agree with him. That's really important to try not to project what you know about something on another thing. The thing you want to know is what is the true nature of the probe you're using. What is the true nature of supernovae and how supernovae behave in nature? And how does your sample representative to this thing in nature? And so what you have here is a table from Romain et al., but slightly extended in comparison to what Dan has presented. And you see here in the nearby, this is what he said, the nearby ones, the color step they are measured is 0.05. And it's non-significantly different than 0. So you can say that this means there is no step in the nearby environment. This is what Dan said. To me, it's also saying that this is completely compatible with the 0.9 steps they have measured high redshift. If you compare nearby versus SNS or nearby versus everything else, it's compatible with 1 sigma. So your null hypothesis is a question of what is your null hypothesis here. Everyone sees a step of about 0.1, say, and then if several samples have seen that with 5 sigma, your null hypothesis anymore is not that there is no step. Your null hypothesis is, am I compatible with other measurements? And this is yes, there is compatible. So nearby sample, here there is no reason to think they don't have a mass step. Even though if we only look at the nearby sample alone, we cannot say anything. But here there is no reason to believe the nearby sample is anything different, given the data we have. Okay. So I mentioned the global mass step too. And so actually, you can explain the mass step with this local environment. So actually, as you may know, galaxy properties are correlated. And so the global mass, if you have high mass hosts, it means it's a really passive environment on average. And this is what we see here. If we plot the color here is, again, the age. Yellow are the old and purple are the young one. We see that in high mass hosts, we are completely dominated by young environment. And this is why we have the mass step to start with. We have the mass step because in high mass hosts, you favor older environments. And this is explaining the mass step. So we learn information here. OK, so let's come back here and see how does this explain the H0 tension, because this is the only thing I think you're interested for my talk. So even though this is really fun. So we have this step here, and the only thing that matters is that actually this sample here is not a random sample. It's by definition a targeted sample. You need to have Cepheids to do this measurement. It's not any galaxy you're observing. It's not a random sampling of the supernovae population. It's a targeted sample designed for this very purpose. And so for that, 100% of them are young. So to do this assessment, we have used galaxy data, which are not H-alpha map, because we can't measure H-alpha with the instrument we have. So the only proxy we have is NUV, and we are working on that to get it better, but it's about 100%. And actually, on the other presentation, I think the Schultz team agree with that. So it's a targeted sample. So here what you do here is not a direct measurement of the luminosity of the type 1a supernovae. It's a direct measurement of the luminosity of the young type 1a supernovae. And if your sample in the Hubble flow have a different fraction of young and old, and there is a magnitude difference between young and old, then if those two things are true, then you're biased. And actually, I've just shown you it is true. So if you correct for that, you can shift the value, the centroid value of H0 from about 70. This is based on the 2018 paper, not the 19 paper. I just updated the figure, but the concept is the very same. You have to shift everything else in the measurement is correct. You only have to shift the centroid value by up to 3%, which is more than all the other error combined. So to do that and really try to make clear, extremely clear on what I'm saying, you only think two things to be true is that there is a different fraction of young star between the Cepheid sample and the Hubble flow sample. Roughly, this measurement, this 3% is assuming you have 90% in the Cepheid and 50% in the Hubble flow. And that there is a magnitude difference, because there is no magnitude difference, who cares? So you need to have a magnitude difference between the young and the old one. And if you do that, you shift H0 by about 70.6. Again, this is not updated with the later version. So they published way too many papers for me to keep up. I'm sorry, I'm slow. OK, so this is not a slide from Dan, but a slide from Adam that you may have seen. And this is another way to present it. This is what a lot of checks they have done, and it's really an amazing work. And they explain that we need to shift by 0.2. So this is 0.2 is if you want to align with Planck. You might not be aligned perfectly to not be in tension. But anyway, this is what they say. That the hosts, if you select host, only using the spiral in the Hubble flow, you don't change H0. And if you select local star forming, and I don't know if they mean specific or not here, but anyway, you don't change H0 either. So the very idea, which is a really good idea, and this is something when we discuss together, is something one should try to do, is to try to mimic the selection function, this is what Dan said, between the sample where you have Cepheid and the sample in the Hubble flow. If you have exactly the same selection function, then you should not have tension. This is a way to say that your fraction of young and old should be the same in both samples. So if the fraction is the same, who cares if you have different magnitudes? Again, you need those two things to be true. So there are several things here to present, and I'm going to start with one. I'm not sure it's a big deal, but because Dan just mentioned, it was actually in my slide. So this is a shoe sample, and you can remark that there are two cases on which you have a pair of supernovae in the sample. So in the 18 calibrator sample, you have two times where you have two supernovae in the same galaxy. So this happened 2 times in 18 cases for the shoes analysis. In ZTF or in any other non-targeted sample, in ZTF, for instance, right now we have 2 cases in 400 galaxy or 400 type 1a supernovae. And we have none if we select to slightly spiral, slightly face-on galaxy. So I'm not saying it's a problem here. Just
Shoes is looking for 40 years.
Exactly. So I'm not saying it's a problem. I'm not saying this. There is a you look longer, and so potentially the same galaxy might have more chance to give you 2 supernovae. I'm not saying it's a problem here. I'm just saying that if you the selection effect is complicated, that the shoe sample is not a random drawing of something in higher redshift because you have a lot of other things happening. So again, I'm not saying this is a problem. I'm just saying that this is something we need to think about, and that selection functions are extremely difficult. And saying that we go for slightly face-on spiral galaxy is my only selection effect. This is not true. OK, let's come back here. So let's imagine now that we are removing the elliptical ones, and H0 is not changing. The only thing it means here is that the supernovae you are removing have the same magnitude as the supernovae that remains. Otherwise, H0 changes. So the only conclusion we can get from that is that the shoes type 1a supernovae do not vary as a function of the environment, because you are removing some part of the environment, and H0 doesn't change. So the only conclusion here is that, well, you may have different selection, different fraction, but there is no step in their measurement. So this is what they actually say, is that it's a completed plot. Here, slide from Adam again, but they kind of agree that you have 100%, 20%, 50% here. H0 is not changing, and this is a part here, and it's explaining actually why, that you have, they look at different things here in the nearby one, and this is the only thing that matters, as Dan said, because it's the samples they have used, and they don't have any significant step here. So in the next 5 minutes I would like to highlight here, because this is a key element, and I'm trying to convince you that they do have an effect, they just don't see it. So let's take the time. So I think we agreed on, there is those 2 things that have to matter. We agreed on this one, so I'm going to skip that. So let's focus here. So just to mind that we have an effect. SNL, SNSDSS has an effect. In the paper from Dan, foundation has an effect. So the question is why, how the shoe supernovae are special? Why the nearby sample is so special that this is the only sample in nature that doesn't have it? Because this is the conclusion they're saying. And what they say is that it's because it's a purely untargeted sample. It's not a purely untargeted sample, while the other one are. So they are not saying that they have more young or old. They're just saying that somehow, because of the selection function, the old and the young one have the same magnitude somehow. Well, it's actually not the case. And to understand that, it's going to be slightly too much astrophysical for you, but I think it's really important that you have to focus for 5 minutes here. So there is different measurements, and all of them have different steps. Okay, this is why it might be tricky. We have a 0.16 SNLS actually have a 7 sigma, but it's actually a smaller step. It's 0.09. Local mass from David Jones is 0.06 or 7. Global mass is 0.08. And they're like, what's going on here? We have all those astronomers doing different measurements. They have different values. How can we trust that? I'm trying to convince you that this is actually all saying the same thing slightly differently. So to do that, I'm going to go back a simple experiment. Let's imagine that this local specific star formation rate is a perfect age tracer, or is a perfect tracer or whatever is the cause of the step, okay? And we are measuring a step. So this is the amplitude of the step, and this is what I'm going to call the percentage of contamination. So what I mean here is that if I have a point from this area, and my SSFI is a perfect tracer, so it has no error, I mean, they have measurement error, but when you said it's young, okay? Let's imagine I have another tracer, like, for instance, the morphology. I've shown you in some case. Two morphologies said I'm twice elliptical, or two of them are elliptical, or two of them are spiral, so they have the same classification. While, for instance, the spiral I've shown you, sometimes it is wrong. Sometimes it is actually an old environment. So it means here that some point here will be put on the other side, right? And it's not just measurement error. It's just that systematically, there will be really precise measurement, but on the wrong side of the area. And if you do that, then you can see that if I'm moving point like that, my step cannot be randomly smaller or randomly bigger. If I am doing wrong measurements, the step can only reduce. Okay? And actually reducing mathematically following this line here. If I have 50% contamination, it means I put half of my point from this side on the other side and half of my point on this side from the other side. So by definition, I'm shuffling everything around. I should have no step, right? And then we can do this measurement by comparing how the specific star formation rate compare and is correlated with other measurements. For instance, the local specific star formation rate, our sample, and the global mass, they are highly correlated, a 9 sigma correlation. Of course, because in galaxy, everything is correlated with everything. And so we have this global mass here and the local star formation rate. And we see that the global mass is giving you the same story almost all the time, except for the points that are off diagonal here. In this case, the contamination, the intrinsic contamination is 20%. But we have slightly better tracer, like the U-R that have been used by the SNLS team. And this one has a smaller contamination, about 12%. Okay? If we do that for a different tracer, U-R, morphology, global color, local mass, global mass, we see that in our samples, they all align here. And I want to highlight, for instance, morphology. It's known for 50 years or 20 years that it's a really bad age tracer. It's the first row of estimates. And roughly, when you're spiral, your stars are young, but you have in spiral galaxy all stars too. And this is showing you that in comparison to the H alpha divided by local mass, the morphology is 25% contamination. So if you only do a selection based on morphology, well, you're wrong 1/3 of the time. And then you see that you're wrong in contamination, so your step you should see, if this is actually an H step, your step you should see is 70% smaller than the true step in your sample. So again, it's not because you don't see it that you don't have it. It's just that you can't measure it with the tracer you're using. You're using a bad tracer, so you have a bad measurement. So we can compare that. This is our sample. And OK, so this is how, if you put now, you use this contamination you have measured, which is given by nature, not supernovae, it's only galaxy measurement here. And you put the measurement from literature, they do align with this expectation we have here. So here is the Roma et al. SNLS measurement. Here is the characterized measurement, the mass, global mass, and this is the local mass from David Jones' measurement here. So you see that we are actually all telling the same story. We are all saying that there is there is a true H step of roughly 0.15 magnitude, and we all agree with that. It's just that we have a better way to measure that. I'm almost over.
Sorry, I meant to make something, but how do you know intrinsic contamination?
So we do forward modeling to try to see, to disentangle error measurement from intrinsic scalar you have to add. And it's ongoing. The paper is in prep. We try to language that a bit. OK. So now in the latest Jones et al., there is a small paragraph for saying, okay, Michael said we have to look at local specific star formation rates, so this is what we did, and we don't see anything. And this is what they do. So actually, they don't have H-alpha because it's actually extremely hard and extremely expensive to get. So they're using another tool to do that, which is SED fitting using LeFar. You can check that in the Jones 2018 paper. And so we reproduce that in our sample, and this is what they say. So when you see here local specific star formation rates, one have to be careful because it's local specific star formation from optical SED fitting, which is pretty bad. And if we compare that, this is the origin of what they conclude that there is no significant step, and that the nearby type 1a supernovae untargeted survey, the one they are using, has no step. This is the origin of this claim. Okay, this you've seen already. Now, we did that too. We have measured the UGR following the recipe, and this is the LSSFR a la Jones, or using SED fitting, and this is our LSSFR. It's extremely bad. The contamination here is 25%. It's as bad as doing morphology. So if you put that back in the plot here, this is where they are. This is a local mass, and this is a local mass, sorry, and this is a LSSFR from SED fitting. So it is in their sample. If you export, the only thing that matters is the true step here in your sample. So if you do this line here, we are roughly in this 0.15 area. I was claiming it is a true thing in the sample. So they do, sorry, they do see it. They do have it. And this is not on our sample this time. We are trying to reproduce our analysis on their sample, but it takes time because we need to take data, which takes a lot of money, which costs a lot of money. But this is actually from their data, and everyone agrees. Basically, they do agree with us, or we do agree with them, or something like that. So it's the only thing that matters is that the Hubble flow sample from their data has a true H step of 0.15 magnitude. I'm over. So again, there is only two things to be true for this H0 step to move my 3% about 670 or 71, depending on the latest combination. The difference of sample you have, the fraction of Young between the Cepheid and the Hubble flow sample has to be roughly 100 versus 50%, and the true step in your sample, not the observed one, the true step in your sample, the true thing that is affecting the different sample has to be about 0.15 magnitudes. If it's smaller, then the effect is smaller. And if we do that, if both of them are true, then it's not from type 1a supernovae and Cepheid, it's about 70. And so I think there is no reason, it's still an ongoing work, and I want to, but I think there is no reason to think there is a tension. It's just there is an environmental bias. And thank you very much.
All right. Thank you, Michael, for a great talk. That's done.
Hey, nice talk. I think you know I have like 1,000 questions. Okay, so yeah, I'll do one. Can you go to the thing where you show the different samples and based on contamination?
Is this one?
Yeah. Okay, so I think you know what I'm going to say. These are different samples. We're not standardizing the same way. I just don't know how these all can be in the same plot. And well, like the two Jones things, I'm not sure if I followed, but I mean, they're both small. And remember, we're not saying there's no step there. We're saying there's some step, it seems similar to other steps, and we correct for mass, so we're already cutting it down. So it's what's left over and how worried about that for H0. So it seems weird that like there's this 0.15 mag number, but no other Roman or anyone is seeing 0.15 mag. So I just don't understand how we could use a different sample and apply some step which is only seen in your data. I can't follow.
Okay. So I'll try to explain a bit more. I know this one is a tricky plot, so I'll go one step back. So the only thing that matters is that to do this y-axis here, okay, I'm staying here. To do this y-axis here, I'm not using any any supernova information, not at all. I'm just using galaxies. And I'm trying to see if I have the H alpha due by local mass specific star formation rate measurement in this galaxy, and I'm using an auto tracer of the same thing, the H. I can use a UV minus R. I can use global mass to probe for this environmental effect. I can use local mass, or I can use SED fitting LSSFR. If I am doing that, then I have different answer because I have different way to measure the same thing. Some tracers are good, some tracers are bad. If I'm saying that I want an H tracer, which is the day of the week, which is annoying because there is 7. But if we use that, for instance, is it a weekend measurement or not a weekend measurement as an H tracer, hopefully I'm going to find 50% here. I should not have a day of the week step. Okay? So This y-axis here is only saying galaxy measurement, how galaxy behave, how galaxy is in nature. Okay, the y measurement here is only purely supernovae in this time. So and it's from the data. So it's how those data. It's really the number from the paper. No. I mean, it's important here. I mean, it's really important to make the point here.
Yeah.
So it is different sample, different data, different technique.
Yeah.
I do agree with that.
Yeah.
So I'm just saying here that in Jones, you're saying that you have a 0.05 measurement using this technique, and this is a step you're measuring. Okay? I'm just reporting this point in this value here on the plot. 0.05, 74, 75, 35% contamination. You do the same thing with local mass, and you say slightly higher. It's actually the only one which is significantly higher, and I do expect that. It's a better H tracer. So, and then you can ask the question, why does Roman see a higher step? Why they just have a better H tracer? It's the only same thing. So it doesn't really matter, because those are self-consistent measurements. It's a step difference, is the magnitude difference following their own pipeline. It's an internal relative magnitude difference between young and old, depending how you cut young and old. Color, global mass, local mass, or SED fitting. Like so here they are self-consistent. I can put them on this plot. But I'm really happy to continue discussions that.
All right. Thank you.
I would like to know a little bit better about this percentage of intrinsic contamination, how you actually get the point on the x-axis.
Okay. So it's actually ongoing, but it will not change by much. So the way it works here is that you have to do a forward modeling, and you assume so far, because we haven't found a way to do that much better, that the LSSFR measurement is a perfect measurement. So in a way, this is a contamination with respect to local specific star formation rate from H alpha divided by mass. Okay. So you assume this is a perfect measurement, and it has error bar 2. Okay. And then the question is, when you have that, how much is the intrinsic contamination you need to have to explain the scatter you have in the off-diagonal in counting for the error measurement you know in both axes. So it's a forward model, assuming this one to be the truth and this one to be the comparison. And then you have to draw that and you converge until you have the good thing. And this is basically a way to see it will be if I have a correlation here, okay, I have to add intrinsic scatter to explain the scatter I see here. And then in this intrinsic scatter, if I randomly draw points, how many times I will be off diagonal, which means that the LSSFR and this comparison tracer give me different answer. And the fraction of that is what I'm calling percentage of contamination. So you see here, there are less points of diagonals than here. So this one is actually better than this one. That's the way to see it. If we have a perfect line, it will be perfect. Or if this line is consistent with error measurement, it will be 0% contamination.
Okay, last question.
I have to leave tonight, actually. If you have a lot of questions at the break, would be nice. I'm sorry.
I don't know if you know the answer to this question, but do you have any idea what is the physics behind this step?
So the short answer is no. The slightly longer answer is, I can plug. The slightly longer answer is that we know that there is young and old populations. The prompt and delayed, I didn't invent that. It's shown by rate of supernovae. So we know that there is two populations of supernovae, one related to young progenitor, that's younger than 500 megayears, and one other, roughly 50% of them, 50% that are redshift that are older than a few gigayears. And the true physics for that isn't clear. It really isn't clear. People say it's different progenitor channel, like single degenerate, double degenerate, for instance, but it is really unknown. But we know there is two population samples. We know that by rate. And the only thing I did here was to identify which is which with this local specific star formation rate measurement.
It has nothing to do with metallicity.
No, most likely not. The LSSFR happens to be independent of dust and metallicity, so we know it's an H tracer. Okay. Thank you very much, everyone.
Okay, let's thank Michael again for the talk. Okay, and the next speaker will be Wendy Friedman, who will keep discussing this H-naught tension.
Thank you. It's a pleasure to be here. There's probably a microphone somewhere.
Michael?
Oops. Did I leave?
Thank you. Sorry. I'll take it.
Okay. That work?
Yeah, that work. Laser works.
Laser works, but not the pointer.
Not the clicker.
Okay. Okay, we've heard a lot in this session about supernovae. We're going to hear about gravitational lensing. We've heard a little bit about Cepheids and...
Maybe your format, I think you are cut on the left. Maybe we should fix that.
Can we check that this is not only the first slide?
that happened before.
All right, so we have a 16:9 versus 4:30.
All right, I bet you. Okay, let's try it to 1 minute.
Okay. So let me just give you a short summary of the talk, which is, I think we've heard alluded to already in the last couple of days. And I'm going to try and follow Francoise and Sylvia's plea to us to not just give a nice, pretty talk, but to talk about the challenges. And I think it's clear to all of us that systematics are the name of the game. I think when we were in the era of a factor of 2 uncertainty and the Hubble constant, those were the easy days. And by easy, I mean it only took 10 years to beat down those systematics when we got HST. But I think we resolved the question of the factor of 2. We're able to measure a Hubble constant to 10%. I think in the last couple of decades, we have measured H0 to 5% or better. We're approaching the 2 to 3% level. But we really are in a systematics limited regime. And the only way that we're going to understand the level of those systematics is to measure H0 using independent methods. So I've spent a lot of time in my career working on Cepheids, trying to understand the systematics in those. What do I worry about? What keeps me up at night? What are the 2 to 3% effects, particularly the unknown unknowns that could be affecting the Cepheid distance scale? Because whatever other effects there may be in supernovae, mass ranges, overlap, et cetera. If the nearby anchors are off, everything moves in lockstep. So we've been trying to develop for the last 5 years or so an independent route to the Hubble constant, independent of Cepheids, completely independent of Cepheids. So we're using red giant branch stars. These are evolved stars with masses similar to the sun or less. They're evolving up the red giant branch. They have degenerate helium cores. When the temperature reaches about 100 million degrees, then because you have a degenerate equation of state, these stars have degenerate helium cores, they can't expand as the temperature is increasing. And eventually, when the temperature reaches about 100 million degrees, you get a thermonuclear runaway. You end up with this helium flash. You don't explode the star. The energy goes into restructuring the star a little bit into the envelope. But what happens empirically is that you lose stars above the tip of this red giant branch. So if you are observing a population of stars in halos of nearby galaxies, the advantage of the halo is that you are not crowded. The stars are not overlapping and blending. The dust is insignificant in the halos of galaxies. The metallicity we can empirically calibrate directly. We can't do that for Cepheids. We have to use a proxy. Where are we? Saul's here. Hi. Haven't seen you yet. And so I think the beauty of the method is that it is completely independent of the Cepheid distance scale. So systematics are completely different. Now, what I will say is that compared to Cepheids, we've studied Cepheids now for decades. We have probed the systematics. We're beginning to do that with the tip of the red giant branch. They appear to be smaller. The precision actually appears to be higher. The scatter in the nearby Hubble diagram is smaller for the TRGB sample than it is for the Cepheids. But this will take, I think, a number of years again to get to. Oh, now it's worse.
Okay, sorry for that.
Okay. We'll try and deal with the cutoff slides. Okay. What I will say is we have calibrated the method using the Large Magellanic Cloud. Large Magellanic Cloud has been studied to death using a number of methods. We're not basing the results yet on Gaia. That's coming. When Gaia comes, we will have better than 1% precision and accuracy for the 0-point calibration of the TRGB and Cepheids. So I think that's a real area of improvement in the future. JWST is going to let us survey out to larger volumes, so we will get more TRGB samples that can calibrate the type 1As. So what we're doing is observing nearby galaxies. We have a sample of 18 supernovae. It's comparable to the Cepheids. Now you have a sample of 19, I think, and so statistically it's quite comparable. Okay, you can probably guess what's on the left-hand axis. It's cut off. And I show this. It's from the ESA Planck website, just to illustrate, one, the tremendous progress that there's been only in the last couple of decades. So we moved from, before here was really a very widespread factor of 2, and now using a number of different methods, including CMB and Cepheid calibration, even the gravitational wave sirens, which you could see with the large error bar here, does not resolve the tension yet. But there has been enormous progress. And I think as a field, we really didn't stop and just take a deep breath and say, boy, we actually really have improved the measurements, and to some level of significance, measuring at high redshift, a redshift of 1100, and measuring locally actually shows pretty good agreement. Sherry is going to talk about the gravitational lensing, strong gravitational lensing. It wasn't on that plot, but I just put that there to show there's another independent means of measuring the Hubble constant locally. So here I'm just dividing where the recent tension really has come from, which is a measurement of H0 using type 1A supernovae calibrated with Cepheids. So starting here with the key project, and mainly by the Shoes group, so Dan and Adam and their collaborators. One point here using the Spitzer Space Telescope to do the local calibration of the Large Magellanic Cloud in the mid-infrared. And those generally have come in around 72 or so, 73, 74 now. And the value hasn't changed much, but the size of the error bars has continued to decrease. And if we look at, oh, this is suddenly working. If we look now at the CMB measurements, so here starting with WMAP and concluding with the CMB measurements from Planck, the value has come down, but the error bars have shrunk considerably. Here's what gravitational wave sirens do for us at this point, and the hope is that there'll be many more objects that will be discovered with advanced LIGO, and that error bar will come down. So at the moment, where we're at, as everyone is familiar with, is the most recent publication by the Shoes group, which are indicating a 4.4 sigma discrepancy. So really, what we're trying to understand is what is sigma. And here's a summary of the CMB and Cepheid supernova calibration. And so the most recent Planck value is 67.4 with a less than 1% error bar, and the Rees et al. 2019 measurement of 74 plus or minus 1.4, which is just under 2%. So if there are no systematics, if you will allow that for the moment, what could it be? And we've heard lots of discussion of it. We'll hear more. Now I am cut off again. But many options have been considered, and none of them come up looking particularly promising. Late time physics doesn't seem to work and fit the well-observed peaks, and combination of BAO, Big Bang nucleosynthesis, and other data with Planck argue strongly that you can't have a funny shape for W of Z, and so on. So recently, people have been looking at additional early type physics. And so prior to recombination, you're changing the size of the sound horizon. People have also considered non-Gaussian primordial fluctuations. But many of these things right now look very contrived. There's no natural explanation for the tension. Now, when I started measuring H0, I had two directors at Carnegie who told me, don't waste your time working on the Hubble constant because we know what the answer is. It's 50. Someone around the hall from me at that time was measuring 50, and we knew the ages of globular clusters. And I think this is an empirical question. The data have to be improved, and we can resolve this tension. But what's required to do that, if there is new physics beyond lambda CDM. And what I would argue is that we need a measurement of the local Hubble constant to about 1%. Planck has set the bar very high. And in my own view, again, we need at least 3 independent methods that are at that level of accuracy to convince ourselves that we have constrained the systematics. And that really was the goal of the key project when we set out. We had 5 independent methods. What we did was we designed the experiment so that the statistical uncertainties in each of those methods was at a 5% level, which allowed us to then explore systematics and constrain them at better than the 10% level. So each with a precision and accuracy of 1%, that's a pretty tall order. Notwithstanding that this was Donald Rumsfeld, I think it's still an important quote. They're the known knowns, the things we know. There are also known unknowns. That is to say, we know there's some things that we do know, but there are also unknown unknowns, the ones we don't know. And that really is what we're facing. Now, I come from an institution where someone invented the phrase precision cosmology, and I hope that's not what we're living in. Okay, so Cepheids, huge number of advantages, and I think the reason that they've been used for so long is they really have proved to be accurate distance indicators. And the question is, how far can we push them, and can we get to 1% accuracy? And if not, what accuracy can we get to? They've been studied for a very long time. They're very luminous, so we find them easy to find in galaxies, easy to identify because they're variables. They have a very small dispersion in the period luminosity relation. In the I band, that dispersion is 0.2 of a magnitude. That's 10% in distance. So in principle, if you have 100 Cepheids in your galaxy, you've got a 1% H0, 1% distance. But if we only lived in a world without systematics, we could all go home. The beauty of the Cepheids is you can empirically test for systematics. So we've been doing that for many decades now. For example, metallicity. And I'm not going to go into the physics of the PLC relation, period luminosity color relation, but that's well understood. And we project into the observational plane. This is a sample in the I band, 8,000 angstroms from the HST key project. And Reese and Skolnick and their collaborators have used HST to really extend the Cepheid distance scale out to hosts that have type 1a supernovae. But you can see that as you go farther in distance, so here's the Large Magellanic Cloud at 50 kiloparsecs. Scatter is small. By the time you get out to 7 megaparsecs, this is the Maser galaxy, NGC 4258, scatter already has increased quite appreciably. And you can see that the scatter really is large, and I think George's point about what has been emitted, taken out of the PL relation, that it's hard to estimate what the overall uncertainty in the fitting is. Nevertheless, it's a huge amount of work that they've put into this, and they've made the data accessible to the community. Now, again, in the spirit of George, let's look under the hood a little bit, and where are the challenges in obtaining high accuracy with the Cepheids? Metallicity effects. We can't measure the Cepheid metallicities directly. They're too faint to get spectra. We worried about that prior to the key project, and what we came up with was an idea of using H2 regions as proxies for the abundance. You look in regions where the Cepheids are found, you see what the H2 oxygen to hydrogen abundances are, and you can test for metallicity effects. They appear to be very small in the infrared, but it's something that you have to worry about. The reddening is large in the disk. You need very accurate colors. You can form reddening-free colors, that is, take out the reddening, compare local samples and distance samples, and a combination of filters that let you do that, but you need very accurate colors. Whether you correct for reddening or not, these sit in the disk, and it requires really accurate data. Hard to do. We haven't even considered stellar evolutionary effects. The Cepheids cross the instability strip, the models show, several times during their evolution, and there's probably a mass metallicity relation we haven't begun to explore. There are small numbers of galaxies. Supernovae are rare objects, so we just don't have very many of them. And I think probably the biggest issue now is pushing out with HST because supernovae are rare, and in order to decrease the numbers, you have to go farther and farther out, is the crowding and blending. What's doing the crowding and blending? In fact, it's the red giant branch stars and asymptotic giant branch stars, even brighter than the giants, that are in the disk, particularly in the near infrared. So that remains a challenge. Okay, the tip of the red giant branch, not as well studied yet, although they've been known for a long time. And as I explained while they were trying to fix my slides, the evolution of these stars has been well modeled by many groups over many decades, and the helium flash, bolometric luminosity, is really well constrained. It's essentially constant. That's not true when you observe with different filters. The I band, the bolometric correction, essentially cancels out, but we can calibrate the effect with color or metallicity empirically. So where a giant lies in the color magnitude diagram is a direct reflection of the metallicity. It's responding to the metallicity in the atmosphere. Okay, I'll skip very quickly over this just to say that we've been observing with a number of facilities from the ground and also space and trying to calibrate Cepheids. RLI stars, I won't talk about those today, but they also are an independent test of the 0 point, the tip of the red giant branch, and type 1a supernovae. This is our group involved in the study. Very fortunate to work with a very talented group of young people and not so young people. Okay, so advantages of the tip of the red giant branch I pretty much covered, but they are simple. We find them in the halo. The reddening is low. Metallicity effects can be calibrated. They don't have to be followed up for variability. It's very small. And we can find them in galaxies of all types, all inclinations. We don't have this mass range problem or mass step problem. Ellipticals and spirals, all inclinations. So that's an advantage at the moment. The challenge is they're fainter than Cepheids. That's not a practical problem because for Cepheids you have to have at least a dozen observations to measure the periods. So in fact, you can co-add the frames when you use HST to measure Cepheids, but in fact you don't wish to be working in the disk because that's where the dust is high and AGV contamination. But it costs no more than observing the Cepheids. Directly calibrate the metallicity. The dust in the halo is low. The dust in your nearby calibrator, that right now is one of our biggest systematics, and we've got a program now to address that, but that's something that we need to put more attention into. Small numbers of calibrators as comparable to Cepheids, but still small, and the 0 point calibration. That will come with Gaia, will improve with Gaia. So just to give you some indication, here's what you have to do for Cepheids. You're working in the disk. You can see the dust lanes. High stellar density and crowding. We're working out in the halo. That's a huge advantage in terms of accuracy in the photometry. So what we do empirically is measure in the I band again because we see very little effect of metallicity at 8,000 angstroms. But you can see this jump. These are field stars and asymptotic giant branch stars. I'll show you other examples. And what we do is we run an edge detection filter. We're essentially measuring the jump in the luminosity function, the change in the slope, the first derivative of the luminosity function, which we've done numerous simulations. And what I should say is we have not blinded this in the sense of a completely blinded analysis, but every step of the program, different people have undertaken the analysis, and the comparison is only made when the results are in. Just another example of a nearby galaxy. We've also undertaken a pipeline for the reduction of the galaxies. They've all been independently reduced, again, by several different groups. Let me move on because of time. So here's a comparison of the Cepheid distances that have been published as a function of the TRDV distances that have been published. You can see that the agreement is very good over a wide range in distance. The red points here are the galaxies for which we've measured direct supernova host TRGB distances, and that also have Cepheid distances. So the scatter, when you exclude the supernova, the more distant galaxies, actually only 2%, 2.5%. But it increases as you go to the more distant galaxies. The scatter is 0.17 magnitudes, and it's larger than would be indicated by the published error bars for the individual galaxies. So we don't understand the source of that difference right now, but there's something systematic, likely, that is contributing to the differences in the distances. One thing we do notice, if we look at the nearby Hubble diagram, so this is just velocity as a function of distance for the calibrator sample. Here are galaxies that have Cepheid distances, and these are the TRGB distances. We know the total scatter is 0.17 magnitudes. If we just step along and increase the velocity dispersion simultaneously so that we get a simultaneous fit that gives us this observed 0.17 magnitudes, then we find that the scatter in the nearby TRGB sample is smaller than in the Cepheid sample. So they appear to be more precise. Dan mentioned the Carnegie Supernova project. I don't have time to describe it in detail. Probably many of you have seen this before, but it's a survey that we've been carrying, not a survey, it's a follow-up study that we've carried out at Las Campanas over more than 10 years now. I see the light curves are cut off, but you can see the tail end of many different filters. We had 9 different filters, caught the supernovae before maximum, and observed from ultraviolet, which ultimately we haven't used, but BVRI, the Sloan filters, and also J, H, and K. And we've used a program developed by Chris Burns, which he calls Snoopy, for fitting the light curves, and I won't go into detail on that. But also time coverage of the spectra so that we could really get K corrections well observed. We put a lot of effort into studying the systematics and trying to minimize the systematics. So we haven't tried to combine lots of different data sets. These are all taken with the same filters. We monitored the filters over time at Las Campanas to make sure that there were no changes in the filters over time. So it's a very nice data set, multi-wavelength, so we can do corrections for reddening, et cetera. We have continued the project, extended to the infrared using the FIRE spectrograph on Magellan, and going out to higher redshift. That's not yet, most of that's not published, but will be coming soon. So what I'm showing you is going to be based on CSP1. So this project that Mark Phillips and I were co-PIs on. Mark has carried out the extension to the infrared. So here's the Hubble diagram. This is the nearby sample, conveniently cut off, that have the TRGB distances. This is the Carnegie Supernova sample. We've done an MCMC analysis, so we're fitting the light curves with the Snoopy program of Chris Burns, and then used the supernova characteristics to fit for the slope of the color correction, K correction, et cetera, and this peak luminosity and host galaxy mass. In the Burns et al. Cepheid calibration of the supernovae, this turned out to be a big effect because there were no elliptical galaxies in the nearby sample, because Cepheids are found in young galaxies. That's not an issue with the TRGB galaxies. And so what comes out is a determination of H0 in a full covariance matrix. So these are results in the refereeing stage now, so I'm not actually going to present an H0 result to you today. We should have that very soon. I hope maybe the referee's in the audience, so you could hurry up and help us get the paper out, but it's very close. Here we are. Here. In that box. Yeah, we're not out here, we're not out here, I can tell you that. But what I really want to stress again is completely independent systematics. There's nothing in common to the value that we have measured in the calibration, in the physics of Cepheids and tip of the red giant branch, the calibration galaxy we separated, or the supernova sample. I guess, Dan, you've got supernova. You have CSP data in your sample, but it doesn't dominate your sample. Stay tuned. It's interesting. I'll say that. Okay, and I think where the improvement will come in future, and I rushed by this at the beginning, it will be with Gaia. We will be able to get parallaxes. I think, those of us who started out many years ago, the idea that you could get sub% distances, parallaxes to anything was just beyond reach. So the questions of calibration, which are right now the 0 point is one of our biggest systematics, that will be well in hand with Gaia. We right now are engaged in trying to improve the calibration of the LMC, where we're calibrating at the moment, both from the ground and also with HST. That's an area that needs attention. And eventually with James Webb, because these are red stars, we can observe them with JWST. Unfortunately, with the Cepheids, the crowding gets worse because what crowds you again are very red stars, the asymptotic giant branch stars and the red giant branch stars. And the resolution of JWST it's diffraction limited at 2 microns. So it's not going to be a good Cepheid tool. HST was a beautiful Cepheid tool. But it will be very helpful for the tip of the red giant branch. So let me just make a few concluding remarks. I think that, again, as I've said, we need to get at systematics. The only way we do that is to measure things that are completely independent of the Cepheids. We can't rely on Cepheids alone, much as I know and love them. And these are stars that have completely different evolutionary histories, ages, and they're found in different regions in galaxies. The physics of the helium flash versus the pulsation mechanism for Cepheids is unrelated. The lines of sight through the host galaxies, the dust is completely unrelated. So whether or not there's new physics really depends on whether the systematics have been understood and eliminated. 2 remaining systematics of note for us, that's the absolute calibration of the distance scale and the scatter and the small numbers of TRGB and Cepheid calibrators. So I think an unambiguous resolution of the tension really is going to require 1% uncertainty. We need to understand what sigma is. I think the future really does hold a lot of promise, particularly with Gaia, JWST, the LIGO sirens, again, completely independent physics, and strong gravitational lensing that Sherry Suyu will describe in a moment. So I think the measurement of H0 to a precision and an accuracy of 1% is feasible. You're going to need multiple routes to do that, I think. I think it's feasible within a decade, but in my view, it represents a formidable challenge. So I'm going to stop there. Thank you.
Thank you very much, Wendy. Any question? Done? Okay. Michael?
Very nice talk. So one of the tricky bits about the TRGB measurement is reddening. So I hope you could speak more. Do you use like this ogle, or do you do it from the TRGB itself? How do you derive what reddening?
No, we have used the ogle data, and we thank you actually for pointing out the preference for ogle data over other data in the literature. We've devised a method for measuring the reddening for the TRGB stars themselves. It's analogous to what we did with Cepheids, so plotting as a function of inverse wavelength, we can fit an extinction curve, and then we get a direct measurement of the reddening. So, and that's why I say we want to check that again externally. We want to get new data to make sure that we can reproduce that.
Yeah, thank you very much for the talk. I was wondering, I may have missed this, but the TRGB measurement you made, is it only for the supernovae that have Cepheids already, or you have other TRGB? And what's the fraction of your sample that don't have Cepheids?
So because we can observe also in early type galaxies, we've got some S0s, we've got some highly inclined galaxies that you can't find Cepheids because it's too crowded, or you can't find them because there just aren't any Cepheids, as you well know. So about half the sample, 10 galaxies overlap. And there are 8 supernovae. We have some that are in the same galaxy, particularly in the Fornax cluster. So we have 18 total supernovae in 15 galaxies.
Okay.
Right, thanks for the talk. So if I remember correctly from the Burns 2018 paper, only about 5 of the calibrated supernovae had CSP photometry. If that's true for
the infrared.
Yeah, right. So do you account for the heterogeneous photometric systems for the
So
TRP?
we actually have, so the best value that we provide in the paper is based on 18 supernovae, but it agrees well with the smaller sample in the infrared. So we don't see a large difference, and we don't see, the mass range actually really does map rather well. So I think that helps a lot.
All right, if there are no more questions, let's thank Wendy again for a great presentation. And so now we'll have a 1 hour break. We'll start again at 4:30, and I will ask all the speakers from the next session to come and upload their talk. And in particular, for the flash talk presenters, your presentation has to be on the slide before. Okay, thank you so much.
Conference picture. But if Jean materializes, so Sylvia will track him. So just don't go away. Well, if you want to be on the picture.
Cool. Can everyone hear me? Yeah, awesome. So let me start by thanking the organizers for a great opportunity to come here and talk about our work. I'm a postdoc at the Oscar Klein Center in Stockholm. The work I'll be presenting is broadly done in collaboration with people at the OKC in Uppsala, as well as the larger intermediate Palomar transient factory collaboration. This is some stuff on data on the first multiply lensed resolved type 1a supernova. Also some published work that I did with Saurabh Jha at Rutgers and my former PhD advisor, Bruno, who's at ESO. So, wait, is this? Yeah. So over the next about 18 to 20 minutes, I'll just be going through the following. Firstly, I'll be looking at local measurements of the H0. Firstly, at what do the supernova rung of the distance ladder really contribute in terms of systematics? And the way we did this was by looking at type 1a supernovae in the near infrared as standard candles, still on the Cepheid distance ladder, but looking at what the near infrared gives us compared to the optical and whether or not it can be a competitive complement. We also looked at a paper that I did with Edvard Motzell in Stockholm on basically if we were to assume cosmological causes of the tension, where is it that we need new physics? What does this mean in terms of different models? And we tested lots of different physically motivated and phenomenological models, both in the early and late universe. This also was this was preceded by a study that we did looking at relative distance measures in cosmology and basically just using background expansion history to see how can we do like a Bayesian model comparison of different probes. Lastly, what I'll talk about, and this is something that's ongoing work, which I'm super excited about, is time delay cosmography with lens supernovae. So like lens supernovae were the original idea by Refstal, as was alluded in the previous talk. But what I'll talk about is the first multiply lens type 1a supernova. I wasn't going to leave this slide without addressing the issue of why I have a cat on a chair here, but I thought since it's late, this was the last pretty picture that I had when I came to Paris last. So this is Aggie, the cat at Shakespeare and Company near Saint-Michel. And you know, since then, lots has changed, and the prettiest picture that I have on my laptop is this, which is an HST WISP-3 UVIS image of IPTF16GEU. But there's going to be more because there's actual follow-up monitoring, and individual lines of sight in the galaxy actually have extinction measurements. So wait for the next 15 minutes, and slide 18, I think, should have that. So it isn't just a pretty picture, there's science behind this one. Not sure about that. Light entertainment, it's past 5. Anyhow, so very briefly, like motivating why we want to actually do this. We've heard excellent talks in both afternoon sessions. So we see a tension between the inferred value of H0 combining the CMB with BAO and supernovae and the measurement from the late universe here. And with the latest measurements that use like LMC Cepheids along with the revised distance from detached eclipsing binaries, this is significant at the 4.4 sigma level, right? So I'm not going to go much more into detail because we've already heard a lot about this, and I don't think I could do any better. And this is the plot from the Pantheon paper in 2018, and that's essentially what are the current constraints on present-day equation of state of dark energy and its time dependence. And what we find is that while, like with just the supernova CMB and BAO, you have consistency with the standard -1,0 case, there is still a large part of the parameter space that is still allowed, and we still have lots of physically motivated models that before the current state of the art in the data have not yet been excluded. So that's what we want to look at, like measurements of H0, what does the H0 tension mean, both in terms of early time physics, but also in terms of like what can we learn from geometric probes on late time cosmology and dark energy. So broadly, why we wanted to look at them in the near infrared. So this is basically just a summary of like lots of independent tests of systematic effects that could be affecting the H0 measurement. So at the local H0, we have lots of independent studies that did tests of, say, Cepheid systematics, looking at like intrinsic RV line of sight variations, some structure in the PL relation, metallicity effects. They found H0 quite robust to that in Fallen and Knox. There were also like tests looking at, well, if you look at a complicated Bayesian hierarchical model that has a more robust sort of treatment of all the uncertainties, then you still get consistency with the fiducial shoes value. Similarly, the blind analysis that was done with Rees et al. 2011 by Zhang et al. In 2017, that also found consistency with the fiducial shoes value. So what we wanted to see was, what if we replace the supernova rung of the distance ladder that's in the optical with the near infrared? And I'll give a motivation as I move on to why we wanted to do this in the near infrared, why it's an exciting prospect in the exciting wavelength regime. Just to add, like for completeness sake, on the early universe side, I was very excited when I saw both of these papers, where you're replacing the CMB in the early universe with primordial deuterium abundances. You still get that, like, if you combine them with late-time expansion probes like the BAO, as well as independent, like, DES data on galaxy clustering and weak lensing that give you omega m, you do end up also getting this sort of low H0. So you find the early universe points to the low H0, the late universe towards a higher H0. And I think that like the slight shifts between them are a lot smaller than the 9% effect that we see. So that's where like what we wanted to see was, what do we get from the near infrared rung, or like from near infrared observations of type 1a supernovae. So that's the first part of what we wanted to look at. So we've heard from like Dan's talk that like we have a calibration of the absolute luminosity of type 1a supernovae that are in the Hubble flow, so redshift 0.03 to 0.1. And that's done by Cepheid distances in the Rees et al. Like 2016 paper to about 19 hosts of type 1a supernovae. But the supernovae themselves do not come as standard candles. They are standardizable or calibratable distance indicators. So in the optical, what we see is that there's a large diversity in the intrinsic scatter of even spectroscopically normal type 1a supernovae. So that needs to be corrected in order for them to be used as precision cosmological probes. And what you use is things like the width-luminosity relation. So brighter supernovae also end up having a wider light curve because you have more production of radioactive elements, and as a result, you have higher opacity and the photons take longer to leap. We also have relations with the color, brighter supernovae are bluer, and after these corrections, you also find a correlation with host properties. And we've had excellent talks on that like earlier in the afternoon. So basically, you have all these effects. And what essentially is that, so the thing is that all of these effects are empirical, and all of these corrections have been done based on data. What we would like to see is, could we use them as standard candles, which is what, so there's a paper, there's a plot from Casey Mandel's paper in 2011. So this is the peak luminosity versus light curve width relation in the optical, and you see that there's quite a large slope, so you see that they're quite strongly correlated. The red points are the ones that is just the apparent magnitude minus the distance. The black points are the ones with corrections for host galaxy reddening. We find that the difference between the red and the black is quite high in the optical, whereas in the near infrared it's quite low. Also, the scatter here is quite low, and the slope's quite flat. So what you find is that, firstly, type 1a supernova have, like, extinction effects are notorious in terms of systematics in cosmology with type 1a supernovae, because there's a lot of evidence suggesting that supernova hosts have extinction properties quite different from the Milky Way. So if you fit standard Milky Way laws, you get a lot steeper total to selective absorption ratios. Also, convolving that with like intrinsic color effects that we don't really know, that makes it for quite a large systematic. Also, because of the fact that there's lots of debate about the physical origin of type 1a supernovae, in the sense like at what mass do they explode, what's the nature of the companion and the explosion mechanism, it would be nice to have something that has low intrinsic scatter. So when you have an intrinsic scatter that's quite low, you can actually try using them as standard candles and see whether or not that agrees with what you get from the usual approach where you standardize them. Right. So what we did was we did a completely model-independent approach. So as a result, what we find is like we ended up cutting down a lot on like the calibrator sample size, as well as on the Hubble flow sample size. So it's a lot smaller than what the Shoes fiducial analysis is. But what we just wanted to see was like, what do we get if we don't assume a supernova template model? We just use a Gaussian process interpolation to get the peak luminosity redshift relation, as well as like the absolute calibrated luminosity. So combining these two components, we can then get H0 from the near infrared. But what we already see is that the scatter for the Hubble flow is 0.1. As I told you, in the B band, it's 0.5. So intrinsic scatter is a lot smaller in the near infrared. And this does not include any corrections for host galaxy reddening. This is just corrections for Milky Way reddening and K corrections from a spectral template. So that's like the bare minimum that you can do for this analysis. And what, as a result, we found was that H0 from the near infrared agrees really well with the optical. The statistical uncertainty is really small because the intrinsic scatter is really small. So this is of the order 2.2%. We do have systematic effects, and that's mainly because the Hubble flow anchor comes from lots of different surveys, and the CSP and the CFA surveys have a slight shift between them, and that's what we add to this uncertainty. But having a low sigma intrinsic, and if we could get a lot of supernovae on the same sample, for example, like a Hubble flow sample that would be coming out with CSP2, that would be something that's really good in order to like not have these effects, and you can just do them with a single supernova, a single photometric system for the whole supernova Hubble flow. So that's something that's quite exciting. We also find that like there was a study by Burns et al. which found exactly almost the same number as ours, and they had smaller uncertainties because they used a more model-dependent approach, which didn't have as restrictive a cut on the data. And that's something that's quite interesting to see that like different approaches in the near infrared as well ended up agreeing with each other, and that we're moving towards like improving the precision. There's ongoing programs with, or like proposed programs with VIRCAM that we're looking at trying to get like snapshot distances to a large sample of type 1As in the Hubble flow. That's something I'm quite excited about, but fingers crossed that the tag actually gives us time. So moving from measuring H0 and like looking at what the optical versus the near infrared is, to actually like what could be the solution to the H0 tension. So this was using the Rees 2016 value of H0. What we did in a paper with Edvard was looked at lots of different exotic late-time cosmologies. So like biometric gravity here is what's on the left-hand side. The blue line is the fiducial lambda value. And we find that like, for example, biometric gravity is basically a modified gravity model in which like you have two metrics with a carefully constructed interaction term. So the aim is like you can also allow for like phantom behavior. But the supernovae and the BAO are really well constrained what the behavior of this B2 parameter should be. And it's really consistent with its lambda CDM value. So as a result, we don't really get a resolution of the tension. And we used lots of different models, like having negative densities for the cosmological constant, turning off dark energy at a certain redshift. But like none of those models, like if they had a lambda CDM case, they would either go to the lambda CDM case or just not fit. So lots of different late-time cosmologies do not seem to explain the tension. What we did was like a more phenomenological approach in the early universe. So we just added like a radiation-like term to the expansion history pre-recombination. And what we then find is that you can have some amount of this dark radiation, so 10 to the minus 5, which is consistent with like literature constraints from the power spectrum and BBN. And that, at that point, changes like the sound horizon at CMB redshift. And as a result, because that's degenerate with H0, gives you a higher H0 by giving you lower RS. So that was something which would resolve the tension, but since we did like a Bayesian model selection sort of approach wherein we wanted to see whether the additional complication of the model was justified by the data, we didn't really get conclusive evidence. But we said, okay, what if we had the same value and we got it to 1%? Then we started getting like significant evidence that is suggesting that this model would be favored over standard lambda. So it's just adding to the motivation for why we want to get to the 1%. Is it like saying that definitively we would be able to test or confirm whether or not these models are favored over the standard cosmology if we got the local value to 1%. Just an addition to that, that was assuming that the value of H0 doesn't change. So for example, we see small changes like based on the LMC distance changing and new Cepheid observations. So in the event that like that also changes what like your delta H relative to the CMB is, that's also going to like change. Maybe you need less precision. I haven't exactly done the numbers, but maybe like even at a 1.3%, that might start to distinguish that model from lambda. So looking from there to like a study that we did which used only like relative distances both in the early and late time universe. So type 1A supernovae going from, this was while the JLA compilation was still the most recent data, and combining that with the ratio of the BAO to the CMB distance. And the reason why we did this was to have it completely model independent, and then we could like compare lots of different exotic models of dark energy. The first thing I wanted to highlight was there's another like simpler biometric gravity model, which has only one parameter, similar to the expansion history as you'd get from lambda. So this, in that case, it would just be omega m 1 plus z cubed plus 1 minus omega m. This is a more complicated expression, and it fits the CMB BAO ratio for the data as well as the supernovae quite well independently, and it just gives you like reasonable errors on omega m. But when you combine these two, that's when you start seeing like about a 2.5 sigma difference between the values that you get from the different probes, which suggests the combination is really important, because otherwise this would do just as well as lambda in terms of what you get as the Bayesian evidence. But if you combine those two, you start getting this having a lot lower Bayesian evidence than lambda, despite having the same number of parameters. Another thing I wanted to point out was that like this was with JLA, and there's a study that we're doing on like specifically low redshift universe and forecast constraints. But we also wanted to look at what improvements to the type 1a supernova Hubble diagram can do, for example, for distinguishing these models. So the blue line is the Pantheon, the latest compilation, and the black line is the one that was the latest at the time. And essentially what we find is that like this improvement in the type 1a supernova distance, like the distance redshift relation or magnitude redshift relation, is really important, even though it's at the intermediate redshifts and not even at like the highest of redshifts, or like some at the highest of redshifts, plus like calibration has improved significantly. That's really significant when you look at it in this particular model space in order to like start to distinguish this model from lambda. So it wasn't just that model, but like a suite of different models. Hopefully your favorite model is there. They all have, I always get asked what the doomsday model is. It's a linear potential, just in case anyone wanted to ask that. But like, what we find here is that all of these are like dynamical scalar field models, so like quintessence, Thawing quintessence models, which are like moderately disfavored relative to flat lambda. So this is the model that does best. And what we find is that like these sort of simpler modified gravity models don't do really well. But there are some exotic models that still do quite well relative to flat lambda. So in order to like try and distinguish some of these models from flat lambda very significantly, we would either need like a Hubble diagram like WFIRST. So we did some forecasts looking at how well can we constrain quintessence relative to lambda if we had improved Hubble diagrams. But one thing that I'm looking at currently, and like should hopefully by the end of the week be done with this, is looking at whether precision H0 at the 1% level, if it is at the same value, whether that can start to say something about ruling out Thawing quintessence relative to lambda, or whether or not like lambda, phantom, and Thawing quintessence, what is their relative sort of weightage in the Bayesian evidence space if we also include H0, because these were all done with relative distances. So doing them with like absolute distances would be something that would be interesting to look at. So in sort of the second part of this talk, this is something that I'm super excited about right now, is doing sort of cosmography with gravitational time delays, and looking specifically at strongly lensed supernovae. So as Sherry mentioned in her talk, that like there've only really been two systems. So with RefStal, you actually have time delays measured and you can get H0. And the original idea of RefStal in 1964 was basically to use lens supernovae and get like the time delays between the different images. And that's essentially like, so there are two components, one coming from like the geometric delay and the other the Shapiro delay that comes from the gravitational potential. So once you have like the lens mass model and you get time delays precisely, you can then get H0 from the time delay distances. Now, what's interesting in the comparison is that, like, because type 1a supernovae, specifically type 1a supernovae, are broadly standard candles. So, like, you can also detect them based on, like, time domain surveys and just seeing supernovae that are a lot brighter than what you expect for the median magnitude of the 1a distribution, with some like spread of 0.3 to 0.5 mags, but also because they are a well-studied family of light curves like these. So like in the optical, they have a 20-day rise and then they fall from peak. You can actually get very accurate time delays just like by monitoring something in a few weeks to months time scale. So while they're rarer, when you, like if you do find them like getting time delays is something that's a lot more sort of, or a lot less time consuming in terms of observations, but also because like they're transients, you can then get post-explosion reference images that I'll show so that you can like cross-check lensing models. Also their standard nature means you can like, the degeneracies like the mass sheet transformation can also sort of be broken if you know like what their absolute magnification is by knowing what their intrinsic luminosity is. So getting to the system that has pretty much like taken up the last few months of my life, it's super cool because you couldn't really resolve this at P48 in the so the intermediate Palomar transient factory survey, which was a 7 square degree survey. So it's still like quite wide field of view, but it's not as wide as what we're currently doing, which is its upgrade, this wiki transient facility that I'll just talk about in like the outlook. But what was seen was that like this supernova, essentially a spectrum with like a 1.5 meter telescope, was like a complete Borg normal type 1a that is was a nearby supernova in M101, but it was redshifted to the host galaxy redshift of 0.409. Also comparing like the absolute luminosity to the absolute luminosity of the sample of known cosmological or well-studied normal supernovae, it was about a 30 sigma outlier because it had a magnification of about 50. And that was something that like sort of started everyone wanting to get more follow-up spectroscopy. What you could see was that with the 200-inch in Palomar, they got a spectrum where you could see 2 sodium absorption lines, one from the host galaxy and one from the lens. And that essentially was something that triggered people to want to get resolved photometry. So there was photometry with Keck that was done in AO mode, but also HST was triggered. And these are the light curves that we have for the resolved supernova images. So this is a combination of the RGB image made by Joel Johansson, who's at Uppsala, and so this is a combination of the 475, 625, and 814 filters on HST. So these 3 filters. And what we find here, firstly, is that like the model prediction suggests that it's a very symmetric configuration. That's what we also see. And that would lead to a very small time delay. So the time delay that we find between image 1 and 3 is the highest time delay, but that's like 1.5 days. Because it wasn't scheduled around maximum, we don't have very precise constraints. So the uncertainty is also roughly of order 1 day. So that's not very precise in order to then be able to get H0 from this kind of a system. But this isn't really the system that like we're looking at in order to do H0 with. There's lots of predictions done by people at like Berkeley, now Caltech, like Danny Goldstein et al. On like the kinds of images, kinds of systems we'd expect to see with future surveys like LSST. For this, however, what is interesting is that we can measure the extinction in individual lines of sight. And that's quite important, firstly, because we see that like the lens model predicts that these images should be of similar brightness, but image 1 is a lot brighter than the rest of the, a lot brighter than image 4. So this is roughly a factor 6 discrepancy. Even if we account for the fact that image 4 is a lot more extinguished, we're not able to have similar peak luminosities for these different images. So that is probably suggesting that there's some substructure that's leading to some micro or milli lensing beyond just the lensing macro model. This is sort of the amplification distribution. I'm not sure if this axis is very clear, but so this peaks roughly around like 65 to 70. So the value is like 68 plus minus 2.5. And so it's been really well pinned down because of the fact that we have multiple images in multiple filters. So we have the UV, like at least the B band rest frame all the way up to something like J band in order to pin the entire extinction curve fit. So we can account for all of the differential extinctions and then get accurate amplifications of each of the images and therefore the accurate total amplification. That's interesting because, well, right now, like selection effects could be a major part of this, but we've only really seen this at like a magnification of 68, but we've really not seen anything that is magnified by like 5 or 10 or 15 times. And like something that's like magnified by about 5 should be 1,000 times or more more likely than this event to be seen, because that's the predicted amplification distribution from GR. So if we were to find like something else that's like this, that would be quite interesting in terms of like being able to test different theories of gravity. And like I also think it's quite cool that like we can, at a redshift point too, we can measure extinction properties in different lines of sight within a galaxy using the supernova. So I think like in combination between like the lensing magnification, the individual sort of image discrepancies and what that means for like any additional sources of lensing, as well as extinction constraints, this is a super cool system in order to like measure lots of different things, from like tests of gravity to like dust properties. So what we would like, and this is the upgrade from PTF. So this is ZTF, which is 47 square degrees, and it runs at a rate that's about 15 times that of IPTF. The expected rate is about a few supernovae, lens supernovae, including like all types, a year, and we hope to find some by the end of the survey. For LSST, the rates are of order a few hundreds in the survey lifetime, I think. And yeah, the only thing is we really want to be ready to schedule them so that we can get maximum light observations to accurately get those type delays. So that I'll leave my conclusions, and thank you for your attention.
All right, thank you, Subel, for a great talk. Any question?
Yeah, I just wanted to point out a big fan of the infrared, and carrying out the recalibration of the Cepheids in the infrared, I think, is the way to go in terms of systematics. But I think it's important to point out that in a lot of studies that got mentioned today, so Feeney et al. And Zhang et al. And yours and Burns and we et al., you started from the same source of Cepheid distances, and sort of related to what George raised earlier. Everybody's using the same what got rejected in that sample. And when the scatter gets large, as you see for some of the more distant and more crowded galaxies, it may work to be working in magnitude space and doing a 2.7 sigma symmetric rejection. But if you're trying to go for 1 or 2%, that is tough. And it may be like photo-Z's, that when you're wrong, you're catastrophically wrong, and when you don't know what got rejected, it's very difficult to disentangle. So I just want to make the point, it's not surprising they all agree, because they're starting from the same place.
I agree. I think I should stress more that like the main thing was just to see whether something non-standard in the supernova rung is the one that's actually causing some change. Sure. Right.
So, quick question about the time delay of IPTF 16GU.
Right.
Did you take into account of microlensing in the delay?
No, so the delay fit was done just assuming that they're all 1As with differential extinction, but the same extinction in the host galaxy, and then just moving them.
Okay.
So we didn't account for microlensing as of now.
Okay, I think you might have to be careful, because supernova will be microlensed substantially.
There are indications, like I mean, there's a dip sort of in the 625 in image 1. But the thing was, like, there was the Bonnois paper that looked at microlensing and how that could affect. I think that's a lot more subdominant to the errors in the time delay that we get. So, like, if this was like an error of 1/10 of a day, we would have then refit this with like accounting for microlensing, but like we can't really do H0 with this. So that's why like we said that we noted that like it's the microlensing is a subdominant error to what we get from the fit. So yeah.
Actually, it's a similar question that I guess in this particular system there is a significant microlensing, isn't it? Brightness variation, or
I mean,
so it's been measured by the Keck. They have seen the microlensing effects in it. So
right.
how it will affect your H0 values and all?
Right. So, sorry. So likely that there, like if you fit the macro lens model. For the best fit slope, it fits image 1, so that, and it says that all the other images should be the same. So because images 2, 3, 4 are like fainter, that would say that there's some substructure that's demagnifying it. But again, I think the thing being that the time delay itself, like it's literally, you can see them as almost aligned here. Even if you do it like from the near infrared second maximum, the time delay is still consistent with 0 at 2 sigma. So I don't think like these are not the systems you do with like do H0 with. So yeah, I mean that would just add to the uncertainty budget, but like I don't think we could do H0 anyhow.
All right, let's thank Subi Lagan for a great talk. And so the next session will be challenging. So we have 9 flash talks in 35 minutes. So we are going to do 3 minutes per talk and 1 question per talk. And I will ask the speakers just to be ready when their time comes. And the first speaker will be Anna, who is... Yeah, come along, please. Okay, so Anna Zoran.
I'm not sure we're going to do questions. I don't think.
Okay,
yeah.
we'll see what goes. Okay,
sorry.
All right.
Yeah. It's going to be really long to do questions. Huh? Yeah, it's more fun.
Oh, yeah. Okay, you can hear me? Okay, so as we have seen in many previous talks, galaxy clusters are a powerful tool to constrain cosmological parameters, and Planck has detected many of these galaxy clusters distributed over the full sky. And this makes a Planck cluster sample a very good basis for cosmological investigations. But before we can dive into these big questions of cosmology, we need to ask ourselves one smaller question, and that is it a galaxy cluster or is it not a galaxy cluster? Because only if we understand the selection function of the Planck cluster sample can we properly use it for our cosmological quest. However, the follow-up of these Planck cluster candidates is still incomplete, especially at high redshifts and in the low SZ significance regime. So on our poster, we show you how we tackle this problem for a small subsample from the Planck SZ survey. So we start out by showing you our sample, which focuses on candidates at high redshifts and low SZ significance. And we show you how we measure the photometric redshifts and richnesses from optical data. We can also infer the SZ-based mass from the Planck maps with the prior knowledge of the optical center and the photometric redshift. And then finally, we present to you our cluster confirmation strategy. This is largely based on a scaling relation between the optical richness lambda that we get from the optical data and the SZ-based mass. And we basically confirm those cluster candidates which are at least half as rich as expected given their SZ-based mass from the Planck maps, and assuming that the scaling relation applies to these cluster candidates. Yeah, if you're now interested, we're very happy to welcome you at our poster, and thank you and goodbye for then.
One quick question. All right, let's go to the next speaker. So, Inigo. Yeah.
Right. Thank you very much. I'm a PhD student at the IOA in Cambridge, working with Anthony Chaliner, and I would like to quickly advertise our recent cosmological analysis of the Planck galaxy cluster sample with CMB lensing mass calibration. So as most of you probably know, the Planck 2015 SZ counts analysis with CMB lensing mass calibration yielded cosmological constraints, shown here in dark blue, which are at a certain tension with the constraints from the Planck primary CMB, shown there in light blue. So we decided to revisit this analysis. First, we measured again the CMB lensing signal of most of the galaxy clusters in the sample, the so-called MMF3 cosmology sample, which consists of 439 galaxy clusters, SZ-selected galaxy clusters by Planck, using a better CMB lensing mass observable than the one used in the Planck analysis. Then we fed our CMB lensing SZ and redshift measurements to a likelihood that is able to jointly constrain the mass bias parameter and cosmology, in particular omega matter and sigma 8. And that properly accounts for selection biases and selection effects, some of which weren't properly taken into account into the Planck analysis. We found a significant loss bias parameter of 0.71, which is consistent with a number of galaxy weak lensing calibrations of this parameter, and cosmological constraints, shown there in red, which are in agreement with the cosmological constraints derived from the Planck primer CMB. No any evidence for tension. So if you'd like to learn more about this analysis, please do come talk to me and have a look at my poster tomorrow and on Thursday. Thank you very much.
Next speaker is Clara Berges, Polar Bear. Oh, did I misread? Sorry. Clara Berges. Clara?
Can you hear me? Yeah. So, hi everyone. I'm going to give you a brief overview of the Polar Bear Simons Array project, which Suzanne has already introduced yesterday. So, it's a series of CMB polarization experiments located in the Atacama Desert in Chile. So, Polar Bear 1 was a single telescope operating between 2012 and 2017 in only one frequency band and a bit more than 1,000 detectors. We observed both large patch and small patch in the sky. From small patch data, we published results concerning CMB polarization and in particular B-mode polarization that you can see just here. And the large patch data are still being analyzed, but we have recently published results of cross-correlation studies with the Herschel Galaxy Catalog and the HSC survey. And most important, we are currently updating our experiment. So we will have three similar telescopes, each of them having more than 7,000 detectors. And most important, we will have 4 frequency bands, which means a much better foreground removal. And once this full Simons array is complete, so far we have already deployed one of the receiver, and the next two ones are going to be deployed later this year. And so when the full Simons array is deployed, we will be able to set constraints on R and on neutrino meshes with the help of other experiments. And it's also important to note that the Simons array will be a non-sky demonstrator of key technologies for the next generation of CMB polarization experiments. So, for example, broadband half-wave plates rotating at cryogenic temperatures and dichroid focal plane that are going to be used for the Simons Observatory. So if you want to learn more about all the cool science we can do with Polar Bear, I will have a poster tomorrow and on Thursday. Thank you.
Thank you very much. Next speaker is Silvia Caprioli.
Okay, so good afternoon. I'm Silvia Caprioli. I'm a PhD student at the University of Milan, and my contribution to this conference is a poster titled Hunting Primordial B-Modes with the Large-Scale Polarization Explorer. So, as you all know, the search for primordial B-modes in the polarization pattern of the cosmic microwave background is one of the most challenging and active fields in modern observational cosmology. And there are a lot of experiments all around the world trying to perform this difficult measurement. LSP is one of them. It is an international project with Italian leadership. And its scientific goals are the measurement of the CMB polarization at large angular scales, and the constraint of the B-mode component down to R 0.03 with 99.7% confidence level, and the production of wide maps of galactic foreground polarization, both from synchrotron and dust. The peculiarity of the LSP experiment is that it is based on the synergy of two instruments observing the same sky region, about 25% of the sky in the northern hemisphere, but complementary for frequency coverage and technology. So on one end we have a SWIPE, a balloon-borne experiment based on bolometers and looking at the high frequencies. Launch is foreseen from Svalbard Islands in winter 2020-2021. And on the other hand, we have STRIP, a ground-based experiment using coherent polarimeters and looking at the low frequencies. It will take data for 2 years at the Teide Observatory in Tenerife, Canary Islands. So that's all. Thank you, and see you at the poster session.
So hello everyone, I'm Florian Keruzore and I'm here to tell you a bit about what we do for SZ cluster cosmology in the NICA2 collaboration. So as you know, the analysis of Planck data left us with a tension between cosmological results coming from the CMB and from galaxy clusters, as you can see on the top in the sigma 8 omega m plane. And so what we do is we use the NICA2 camera at the IRAM 30-meter telescope to get a high-resolution follow-up of 50 high-redshift clusters detected either by Planck or ACTS. So for the beginning of my PhD, I led the analysis of the second cluster of this SZ large program, so from the NICA2 raw data to the SZ map that you can see here, and then to the physical analysis of the cluster. This proved to be quite a challenging analysis because this cluster is the faintest source of our sample. It's the lowest mass we have and the highest redshift, and it's heavily contaminated by sub-millimetric point sources. Nonetheless, I was able to run the analysis and to get its pressure profile, its SZ integrated signal, and its mass, and to combine that with the results of the analysis of the first cluster. Now, of course, we can't conclude anything using only 2 galaxy clusters, but eventually when we will have more statistics, we will be able to get a recalibration at high redshift and high resolution of the mean galaxy cluster pressure profile and of the SZ signal to mass scaling relation. And these are 2 essential tools for SZ cluster cosmology, and so we hope to be able to use that to reanalyze Planck data and see if this can help us with the tension. Thank you.
Thank you very much. Okay. The next speaker will be Abhishek Manyar on a CIB.
Can I change this slide, please? Hello everyone. So I'm Abhishek Manyar, working in Laboratoire d'Astrophysique de Marseille with Guylaine Lagache and Mathieu Bederma on using the CIB as a cosmological tool. In this particular project though, we are trying to measure the KSZ power spectra. Why? Because we know the patchy component of the KSZ power spectra has a potential to constrain the reionization history of the universe, which is not very well known. So the KSZ shows up on really high multipoles in the CMB power spectra, where the foregrounds like CIB, TSZ, and their cross correlation are very much active, and hence they have to be removed for. Now, this has been done before, but what normally is done to account for these foregrounds is we either have assumed a power law or some best fit template from some model, and we fit for a global amplitude on all the frequency across all the frequency channels, which is not an ideal approach. And especially for a foreground like CIB, what it means, like we are assuming the CIB, all the different frequency channels are perfectly coherent with each other, correlated to each other, 100%, which is again not correct. And at the same time, one of the things which is not accounted for is the models which the templates which the templates which are used for the CIB and TSG, sometimes they are not the same ones which are used to calculate the CIB cross TSG template. So there are inconsistencies. Now what we do is we have prepared a physically motivated Halo model of the CIB which works on all the multiples, on all the scales, and we have a Halo model of the TSG. We combine these two Halo models and we prepare another CIB cross TSG Halo model, so we are consistent in that sense. And one of the things which is important is at every step of our analysis while running the MCMC chains, we are varying the foregrounds with the cosmological parameters for that particular step, which is being done for the first time. And on the data side, we are combining the Planck, SPT, and AG data for the KSZ power for the KSZ. And in order to constrain the CIB parameters, we are using the Herschel and Planck HFI data to get better constraints on the CIB parameters. And this is still a work in progress, so results are really expected very, very soon. And so please watch out for the paper. And we hope that an approach like this will be used for future CMB data analysis, where we actually account for the physical models rather than just fitting for a power law. Thanks.
Thank you very much, Abhishek. Okay, and the next speaker would be Ludmila Berdina.
Can I use this? Okay. Good evening, everyone. My name is Berdina Ludmila. My poster will be about the studying of the spatial structure of quasar in gravitational. In gravitational gravitational lensing system, and this is which okay, excellent. So the quasar is very important, very interesting object in the astrophysics and cosmology, and in spite of the huge huge study of this object, the spatial structure, the spectral features, and others still remain a lot of questions. So the measuring time between, sorry, little bit nervous. The measuring time delay between the brightness of the quasar in different parts of spectrum, it's very important that it will be in different part of spectrum, allows us to investigate and make some assumption about the spatial structure of the quasar. This method is called the reverberation mapping, and using this method we determine the time delay between the different light curves in different filters for each images of the quasar. And we find out that the time delay which we obtained differ from the predicted by the standard scene accretion model proposed by the Shakura-Sunayev. And on the sorry. Yes. Okay, it's working. I don't see. On the example of this object, well-known object, the Einstein cross, you can see the image of this object. We obtained the time delay using the reverberation method. On this picture, you can see the light curves for each of these four components in filter R. And also, we have the same observational data for filter V and also filter I, and using that and obtaining the time delay between these light curves and different filter, we get this result. You can see on this table the result which we obtained. For the first, it seems like the normal time delay, but if we're using the standard model of the scene accretion disk proposed by the Shakura-Sunayev and try to, for the same mass, obtain the time delay, we obtained these values. And compare this to time delay, we see that it's enough differ between the big difference between this time delay. So in the work, the Shakura-Sunayev, they proposed the possibility of the existing the supercritical accretion regime, which can lead the existence of the scattering envelopment with this radius. So using this assumption, we we made conclude. Sorry. We made such conclusion. About this conclusion, I tell you near my poster. You can see my poster. I with great pleasure to tell you all the questions near my poster and tell more about this method, which method we use to approach this data. Thank you.
Okay, the next speaker is Jenny Wagner on strong lensing.
Okay, and now to something completely different. Take a look at the picture and try to answer the question, who's behind the tree? The answer is someone with 2 green hands and a green tail, because this is the observational evidence that we have in this picture. Answers like a lizard or an alien might also be true, but they include further assumptions and they are based on prior experiences. So we cannot decide who's behind the tree, but we can use the observational evidence that we have in order to infer some properties of the guy behind the tree. For instance, it might be a reptile because we have the skin structure which we see here. So this is a very down-to-earth example, I know. So let me come to a cosmological example which works in exactly the same manner. So take a look at the next picture and try to answer the question, what's behind the gravitational lens? Here we can ask, given the observational evidence from the multiple images that we have, what properties can we infer about the lens and about the background source without using a lens model and without using a source model? So, and furthermore, if we want to pursue this direction of observation-based inference, can we understand the degeneracies that arise in this gravitational lensing formalism to a deeper level? And in particular, what is the cosmological meaning and the origin of the famous lambda parameter in the mass sheet degeneracy? If you're curious about the answers of these questions, I'm very sorry, you have to wait for tomorrow to visit my poster. Thanks.
Okay, the last speaker of this session, I'm Borini.
Okay. So I have just a short research note on how do we measure sigma 8 with various cosmological data. In order to study the source of tensions in sigma 8 measurements, we can consider the physically different independent measurement of sigma 8, which we can obtain from Planck CMB data. First of them, of course, is the detection of signatures of gravitational lensing in Planck temperature anisotropy spectrum, which is observed mostly at high multipoles, higher than say 1000. Also, one can measure optical reionization depths, which fix the amplitude of temperature anisotropy spectrum. Also, we have, of course, the gravitational lensing potential, which is obtained from high-order statistics. So, all of them is shown here, and you can see that 2 of them are consistent, and the 1 of them is in some tension with 2 other. In tension here, you can see in some tension here is the data set on Planck temperature anisotropy measurements at high multipoles. So also we can compare these constraints with constraints from other experiments that are shown here. The data from SPT polarization, clusters, mass function measurements, weak length and matter power spectrum, redshift space distortions, and basically all the data which were available approximately a year ago when the corresponding paper was written. You can see that all of them are in very good agreement between each other, except one. Again, except that Planck temperature anisotropy data spectrum at high multipoles, which is in approximately 3.7 sigma tension with all the data combined. Of course, we cannot combine data which are not consistent between each other because it just makes no sense. But here you can see that many data sets with different physics, different systematics are consistent, except, as I said, one. It is also interesting to note that actually a small additional component which we can add to theoretical temperature anisotropy spectrum can change the constraints significantly. Here is an example. There is no physics here, just a function which which was chosen by hands. But this function is small. You see that at maximum it has maximum around 20 microkelvin squared, which is, say, for example, which is less than the difference between Lmc and Planck. And you can see that if we add this function to the theoretical temperature spectrum, just before the spectrum go to Planck likelihood, the constraints which are obtained from this likelihood is shifted significantly. And you can know that they are shifted to the correct place. And by the way, H0 here is also shifted to the correct direction, to the higher values. That's just an example, but I would propose that one can suspect, based on this, one can suspect that there may be some unaccounted systematics in this data. So my conclusions are as follows. The tensions in sigma 8 measurements emerge due to the only data set, actually, which is the Planck temperature anisotropy data at high multipoles, larger than approximately 1000. There may be some unaccounted systematics, and if this data set is excluded, the tensions in sigma 8 measurements disappear completely, and also the tensions in H0 constraints weaken significantly. So there are also some, I think, interesting results on the constraints on some of Neptune mass, but I have no time to discuss it. So we can find the details in the published paper and, of course, in the poster downstairs.
Thank you very much. All right, let's thank all the speakers from...
On this positive note, that we've spent 10 years doing nothing.
All right, so let's thank all the speakers from the session, as well as Sherry. Thank you for your help.
Yes, that thing.
Finally, actually.